ktoś płacił.
No właśnie, chłopaki, no trzeba przelewać.
Dobra, coś tu działa, mikrofon łapie. Dobra, to ustawię go.
Tak działa.
Dobra. Ty korzystasz z tego, ja po prostu ustawię go w stronę sali, żeby on tak wyłapał ten dźwięk, który ty będziesz mówiła, więc to będzie wszystko słyszalne prawdopodobnie.
Czyli jak mam robić to? Używam
Korzystasz z tego mikrofonu. Nie przejmuj się nim w ogóle. On wyłapuje dźwięk z sali.
Rozumiem, tylko to się nie będzie odbijać?
Nie, bo to nie, bo ja wyciszę tutaj ten, żeby to nie było. Bo to Matiego będzie tak słychać.
Mogą się już pojawić te slajdy?
Tak, ja już pokazuję. Slajdy są tutaj. Ej, no to. Co tego? No, to się tutaj. Te prezentacje chcę. O! Działa. I teraz ostatni test. Masz ten też u siebie? Czy to jest ten?
To miał być na bardziej obskurny.
Działa. Czy muszę kliknąć?
A nie ma wskaźnika?
Nie, to nie jest ten. Chyba jest jeszcze drugi.
Krzysiek używał, był...
Bo jest podłączony, tylko że nawet nie jest. Czy ja muszę go włączyć? A, przepraszam. Zacząłem panikować już. Ups, wibrało. Dobra. Przepięknie. Dobra. Tu ci działa wszystko.
Tutaj nie zauważyłam żadnego zegara, wiesz?
Niestety nie
Ale
ma.
mam telefon.
No dobra, to ci oddaję to.
Jak to jest? Też ja mam 40 punktów, tak mówię. Krzysiek mówił cały swój czas i pytania wlazły na przerwę.
Tak, no więc pewnie będzie dość podobnie.
Ja tego nie przećwiczyłam tak na czas.
Już zaczynam.
Nie wiem, jak to wyjdzie.
No wiadomo, no, im mniej przerwy zabierzesz, tym myślę, że będzie lepiej. No ale masz 45 minut, tak jakby całego swojego refatu, więc możesz cały refatować 45 minut. Nie.
Działało.
Dobra, to ja idę na widownię, jak będą jakieś problemy, to będę biegł tutaj. Postaram się.
Alright, so the next speaker of this session is Katarzyna Kowalik from University of Warsaw.
Thank you. And, thank you very much. Organizers for inviting me here. It's a great pleasure and honor to be with such a great speaker, really. And I'm very happy to visit with you for the first time. So the topic of this talk is the logical strength of crisis conjecture, or some recent advancement about determined strength. So I will start with this stating crisis conjecture, which is really a theorem proven by later, but somehow they conjecture or Fraser state with the statement. So it says that every infinite sequence of countable linear orders admits two indices, I smaller than j, so that the order Li embeds into Lj. In other words, we can say that countable linear orders are a well-fuzzy order with respect to embeddability relation. That means that there are no infinite antichains and no infinite strictly descending sequences. And this is one of now many results in something that we can call quasi-orders theory. Two other famous examples of results in this branch of countable combinatorics are the Kruskal's tree theorem and Graf-Minor theorem by Robertson and Seymour. And this branch of combinatorics is very interesting for logicians because, by the way, can you hear me well? Because I can hear the. Because first of all, this kind of theorems often turn out to require very strong axioms for their proofs. So they provide a bunch of improbability results, which are pretty interesting from foundational point of view. As you remember, Gödel's incompleteness theorem says that any reasonable theory that formalizes some part of arithmetic is incomplete, but with Gödel's result was kind of artificial, not mathematically meaningful. And theorems of this type are often examples of theorems that are unprovable in a stronger and stronger axiomatic system. And secondly, they are unprovable in some well-understood theories of arithmetic, but then understanding their exact logical strength is notoriously hard often. And one of the examples of such a hard theorem to understand from a logical point of view is Fraser's conjecture. And okay, so now, okay, reverse mathematics. So there is a program in mathematical logic which is dedicated to answer this type of question. What are the weakest axioms needed to prove a given mathematical theorem? It might be a theorem from analysis, from algebra, topology, differential equations, and of course combinatorics. And very general methodology to answer this type of question is as follows. So first we choose some base theory B in some formal language L. And this theory in this language must be, well, not too stupid. You may be able to formalize objects, mathematical objects that occur in theorem T, but it shouldn't be too strong, that is, it shouldn't prove the theorem T itself. Then you translate this theorem T into language L, and then you try to prove equivalence, that T is equivalent to some axiom A over the theory B. So this is why we have this funny name reverse mathematics, because if you want to prove this equivalence, we need to prove both sides of the equivalence, and one is to prove an axiom from a given theorem. And now, theorems that we often study have the following format. So every x there exists some y, such that they satisfy some property P, and x and y are often some infinite objects. So the logical strength of such a theorem is connected to how hard is it to find this object y in terms of x. How hard is it to define, to compute, to construct y given an access to x. And thus, axioms that occur in such equivalences are very often so-called set-existence axioms. So this axiom basically say how complicated infinite objects we are allowed to use in our proofs to prove such a theorem. So now this is very general, but now a few words about logical setting of reverse mathematics. Okay. So the logical setting of reverse mathematics is called second order arithmetic. Second order because we have two
types of objects, two types of variables. So variables for natural numbers and variables for sets of natural numbers. And then standard non-logical symbol to speak about arithmetic. Well, let me stress that it is all first order logic. So we have completeness, compactness, Polymerhenheim. This is only to stress that we have objects of second order, but formally we work in a two-sorted first order language. So models have the form, as you can see, and M is just some sets of elements with some arithmetical structure. It might be standard natural numbers, but it might be something bigger. And this handwritten X is just a fixed family of subsets of M, and usually it is enough to work with countable models, that is M and X are countable. So when we quantify over sets, we quantify only over this X and not over the whole power set of M, which makes it still first order logic. And now there are two main groups of axioms that we that comprise theories that we work with. So these are induction and comprehension axioms. So for every formula of this language of second order arithmetic, you may write down induction axiom and comprehension axiom. And
so the phi is the first order formula.
Sorry?
It's phi first order.
Yes.
So it doesn't include sets.
Well, first order in the sense that the whole language is first order language.
Okay, but you're allowed to use set variable.
Yes. And this is quantifiers, yes. Let me say that the logical strength of axioms is closely related to their syntactic complexity. And syntactic complexity increases with the number of alternations of quantifiers. So in this talk, only this formula classes will be relevant, where we count alternations of set quantifiers. And here, this formula phi in the bottom of the slide is arithmetical, meaning that it does not have any set quantifiers. There is a hierarchy which cares about alternations of number quantifiers, but for this topic it doesn't matter. So just look at these three things. And now, in reverse mathematics, we have something called the Big Five. These are 5 axiom systems in this language of second order arithmetic that have played a really important role in calibrating strength of lots of theorems from very different parts of mathematics. And I'm not going to define them in full detail, because, they consist of some portion of induction, some finite list of algebraic and ordered structure of natural numbers, and a finite list of axioms. But then what differs, what makes the difference in the systems are set existence axioms. So starting from the weakest one, we have RC0, which is recursive comprehension, and this theory states that computable sets exist. And basically, these are the simplest sets that we work in this setting. Then we have WK0 for weak Koenig's lemma. It says that infinite paths in infinite binary trees exist, and this system is definitely, it's strictly stronger from RC0 because there are infinite computable binary trees, such that no infinite path is computable from this tree. But this is for, we say it's conservative over RC0 for a really big class of sentences. Then we have ACA0, arithmetical comprehension axiom. It says that sets defined by arithmetical formula exist. That is, you may define sets by formulas which don't quantify over sets. Only number quantifiers are allowed.
Then arithmetical transfinite recursion, which says that you may define sets by arithmetical formulas, but you may repeat the process or defining set along any well-order that happens to exist in your model. So in ACA0 you may repeat inductively arithmetical definition only finitely many times, whereas here you may repeat it, you may go transfinite. And then pi-1-1 comprehension, which is a simple definition, it says that you may define sets by pi-1-1 formulas. So one set quantifier is allowed. And we'll be concerned with the fourth and the fifth theories that are in red. So, no, I'm not going to read this. This is just for those of you examples of what kind of results people are looking for in reverse mathematics. These are kind of classical examples, and it shows that like we have a kind of remarkable phenomenon. So it turned out that theorems from as different parts of mathematics as analysis, topology of separable metric spaces, countable algebra, descriptive set theory, partial differential equations, mathematical logic itself, they turned out to be equivalent to, well, even provable in RC0, which are not many theorems, but then many theorems turned out to be equivalent to only one of these four systems. This is why we call them Big Five. And, well, let me know, maybe comment, well, how can we speak about so diverse mathematical objects in this one language? Well, by means of coding. So you may, any finite object can be coded by a natural number. So you say, for instance, when you prove Gödel's incompleteness, you do arithmetization of syntax. You assign numbers to formulas, and of course you can assign numbers to finite graphs, to finite trees, whatever you like. And then for countable objects, you may encode as a subset of natural numbers. And also you may encode a countable collection of countable sets as one countable set by pairing function. And not like by WKL0, the last theorem is compactness or first order logic. So in reverse mathematics, we also study logical strength of theorems from logic. Later you will see some formalized logic as a axiom of the theory that I will try to describe to you. So the string of phrases here, conjecture. So where does it lie in this hierarchy? So long ago, it was proved by Richard Shor that a phrases conjecture implies ATR0. Pretty long ago. Then, pretty recently, Antonio Montalban showed that it is provable in pi-1-1 comprehension. So the original proof by Richard Leiber was kind of easily formalizable in a super strong system pi-1-2 comprehension. And Montalban's work was really remarkable because he had to find a completely different proof of this theorem to go through in a weaker system. So this is what you can sometimes see in reverse mathematics, that to really calibrate strength of a given theorem, you need to find a, in a way, simpler or maybe more elementary proof. Doesn't always mean that it's conceptually simpler or simpler for a human to understand. But now, this upper bound of pi-1-1 comprehension, we know in advance that it cannot be optimal. Because the thing is that phrases conjecture has complexity pi-1-2. It says that for every sequence of linear orders, there are two in this sequence that there exists embedding. It's pi-1-2. Whereas pi-1-1 comprehension is only pi-1-3 axiomatizable.
because it proves consistency of all its pi1 consequences. So for Gödel's style reasons, you cannot have equivalence of Freise's conjecture to pi1 comprehension. And recently, Anton Freud gave a better upper bound for Freise's conjecture. Namely, he showed that it is provable in a certain system that we denote pi11 comprehension gamma of partial predicativity. And well, of course, I will explain this system in a moment. But firstly, well, we have partial impredicativity. But first, what is impredicativity? So pi11 comprehension is a canonical example of an impredicative axiomatic system, actually one of the weakest impredicative theories that we work with. And so consider it's defined in axioms, some pi11 definition of a set of natural numbers. So this is impredicative definition because to define the set S, you need to quantify over all subset of natural numbers, including the set S itself, and some other sets that are definable from S. So you haven't constructed the set S yet, but still you quantify over it. So this is kind of circular. It's called impredicative. And next, okay, examples. So an example that all of you know is like from first year algebra course book. Algebraic structures sometimes are defined as intersections. So a subgroup of a given group that contains some elements is defined as the intersection of all subgroups that contain those elements. And this is pi11 definition, but of course you can define such an algebraic substructure from the bottom up recursively. So it's not a genuine pi11 object. But then, given a linear order, you may consider a well-founded part of it. And this is a genuine pi11 object. So we will use this later, as you will see. Okay. So, as I said, pi11 comprehension is not pi12 axiomatizable, but it has many interesting pi12 consequences. And for the reason that I mentioned, it is we know that any pi12 consequence of pi11 comprehension must be provable in a weaker system. And there are many pi12 theorems, often from combinatories, like Freise's conjecture, that are either known to be unprovable in ATR0, or at least Freise's conjecture not known to be provable in ATR0. And to calibrate strength of this type of theorems, Henry Tausner introduced something that he called theories of partial impredicativity. So he defined some theories that are pretty similar to pi11 comprehension, but they are not full pi11 comprehension, but say more like smaller part. Like he used some equivalences, some characterizations of pi11 comprehension. For instance, pi11 comprehension is equivalent to the leftmost path principle. It says that every infinite tree has a leftmost branch, and he considered axioms which says that every infinite tree has a arithmetical leftmost branch. That is, there is no branch on the left from this branch that is arithmetically definable. This kind of weakening of pi11 comprehension, but we won't go into that deeper. Recently, Yudai Suzuki and Keita Yokoyama introduced a whole hierarchy of intermediate theories between pi11 comprehension at ATR0 that exhausts all pi12 consequences of pi11 comprehension. And our theory that we studied lies precisely between the first two stages of this hierarchy. So by the way, this, as far as I remember, Henry Tausner showed that certain pi12 theorems like Kraskow's theorem, Nash-Williams theorems, he bounded them by some of theories that he introduced. So now Anton Freund added the case of Freise's conjecture. Okay, so here is the definition of our system, pi11c gamma. It consists first of AC0 as some basis that we need to have to work with with stronger theorems. And then it says that every set X lies in some countable coded omega model, satisfying ATR0 and pi11 comprehension relative to this set X. So here, this is some explanation, but well, it doesn't really matter for us what this countable omega model is, but just recall that in second order arithmetic, we may speak about very different mathematical objects, including models of arithmetic itself. So a coded model is just one set from the point of view of our theory of some grand model, if you prefer, which, if you look at it, this is from set Z, if you look at it as a set of pairs, what you can always do by pairing function, then you see that it calls a countable family of subset of natural numbers. Okay, and pi11 comprehension relativized to X is just comprehension axioms for all pi11 formulas with X as the only set parameter. So we weaken pi11 comprehension considerably. So this is why it's called a theory of partial impredicativity, because we have only part of this strength of pi11 comprehension. And our result goes as follows. So we prove that this theory pi11c gamma is equivalent to.
Sorry, but you're allowed to use X to define X? So it's the same X?
No, so there is this like straight X, and there is where? And you have this like kind of handwritten X.
Yeah, but pi11 is the X. So this X is the same X?
Yes, because it means, well, we are given the set X, and we are allowed to define any set by pi11 definition with X as the only parameter. Well, of course, X is definable from itself. And the main result is a characterization of this, well, maybe not that nice looking theory in terms of something that proof theorists have a good grasp. So we characterize it in terms of well-ordering principle. So this is the statement that the transformation, this is transformation of linear orders that you can see, preserves well orders. So a word about well-ordering principles. A well-ordering principle is the statement of the following form, that for every linear x, if x is a well-ordered, then so is d of x, and here d of x is another linear order, computable from x, and usually it is represented by a term system built from elements of x. And here you have a canonical example, which should look familiar to all of you. So, given a set x, we build a set of formal sums which look like pretty Cantor normal form, and with the usual order on such an object.
And the statement that this transformation preserves well-all orders is equivalent to ACA 0 over the base theory RCA 0. So this is a pretty classical result. And now there are many more results of this type. Also ATR 0 is characterized by a well-ordering principle and many other arithmetical theories. But our result seems to be the first that links well-ordering principles to theories of partial impredicativity. This is a novelty. Well, it is a novelty because the hierarchy of partial impredicativity is a pretty recent thing, but it might be a good starting point to investigate theories of partial impredicativity in the future. And to give you at least intuitive sense of what is our well-ordering principle that we worked with. This is a pretty strong principle. I need to tell you a little bit about ordinal functions because as you could see from this example, of course it's connected to the ordinal exponentiation. So let me say just a few words about ordinal functions. We have exponentiation with base omega. And this is normal function, which means that it is strictly increasing and continuous, and thus it has unboundedly many fixed points. The least one, epsilon 0, is like pretty famous ordinal. It's still very small from some point of view. And you should associate this ordinal with PL arithmetic. This is proof theoretical ordinal of PL arithmetic. And okay, we have unboundedly many fixed points, so of course we may enumerate them in increasing order by ordinal. So we get another function, and which lists all epsilon numbers. And this is also a normal function, so we can enumerate its fixed points again. And in fact, we get a whole hierarchy of functions that are obtained by enumerating fixed points of the previous functions. So we start with ordinal exponentiation with base omega, then as successor stages we just list all fixed points of the previous function, and at limit stages we list all common fixed points of all previous functions. But well, pretty nice. We think that we can reach very large ordinals in this way, but not really. Because because we can consider the following function, and it turns out that it is a normal function too, and it also has many fixed points. The least one, they are enumerated by gamma function. The least one is called gamma 0, and this is proof theoretical ordinal of ATR 0. But I said we cannot really get far with describing ordinals in this way because, well, gamma 0 is closed under Veblen functions in this sense. So you cannot give a name to gamma 0 in terms of Veblen's functions in smaller ordinals. We reach some limit of how we can define ordinals, and proof theorists to measure strength of stronger theories than ATR 0 have to devise more smart ways of naming ordinals. Okay. So now the order that occurs in our main result. So you see we have this gamma. So the ordinal function gamma can be generalized to a computable transformation of linear orders. So we may define object gamma x, well, not only for an ordinal, but for an arbitrary linear order. And this will be just a term system where we use Veblen functions and elements of x as constants. So these are some formal terms. We may define recursively order on this term system. And yes. And this is linear order, and it will be a well order if x is itself a well order. Now we have another symbol, omega. Omega is a symbol that appears in ordinal analysis of impredicative theories. And here it is just a symbol that intuitively refers to a very large ordinal with very strong closure properties, much stronger closure properties intuitively than gamma zero, say. And there is a proof theoretic, set-theoretic construction linked to this kind of ordinals where omega is interpreted as a first uncountable ordinal, but when we define this first term system in arithmetic, this is just a symbol, just some intuitions. And now we have also psi, which is a so-called collapsing function. So it comes from ordinal analysis of impredicative theories too. And what do we collapse? Well, we collapse intuitively some huge uncountable ordinal linear orders, gamma, omega plus x, into something countable, much smaller. And function psi, if it has to be order preserving, then it necessarily has to be a partial function. But I don't suppose that you will just understand this slide fully, because, well, what we really work with are some complex recursive definitions of term systems. Well, I think that when we really have a good grasp on what it really means if somebody goes through a real ordinal analysis of something like pi-1-1 comprehension. Okay, yeah, but this is just to show you where objects and ideas come from that we work with. So this collapsing is a technique that whose aim is to get names for very high countable ordinals that correspond to logical strength of some pretty strong theories, for which objects like gamma zero are much too small. And okay, so I'm pretty close to the end, and I think I will fit in the time slot, which is surprising. So how do we prove the equivalence? So recall this theory pi-1-1 comprehension gamma, and now you may well, this is the same gamma that occurs in gamma zero ordinal, because we have ATR zero in this theory. So this is why we have this gamma. So we are given an arbitrary well-ordered X, and we want to prove that this order transformation psi gamma omega plus X is also well-ordered. So in fact, it was not difficult, but it's enough to show that this huge linear order omega is a well-ordered. So it's a well-orderedness of this, and this is equivalent. So we reason by contradiction, and we take some f, which we assume that is strictly the same sequence in omega. And now the crucial thing, we use our axiom pi-1-1 gamma c0. So we take an omega model L, which contains omega and capital omega and f, and satisfies comprehension about those two guys. And then we can define well-founded part of omega. This is, as I said a few slides ago, this is pi-1-1 definition. And we can form this well-founded part only in this omega model and not in our ground model, because there we have only AC0. And then we just, by some manipulations, not that difficult, maybe one page proof, we show that actually omega is equal to W, contradicting the choice. So this is easier part of the equivalence. Now the other direction is proving pi-1-1 gamma from this well-ordering principle. The first thing that we did, we reformulated this theory in terms of inductive definitions. So we show that omega models, well, working in the formal theory, we show that omega models of pi-11 comprehension gamma are essentially models of certain theory ID gamma, where ID is inductive definitions. And theories of inductive definitions are really nice to perform ordinal analysis. And they are very important in this part of proof theory. And they also measure different levels of impredicative strength in foundation theories. So then, how one can show that some theory has a model, omega model, where often by kind of completeness, we prove some kind of Schoenfeld-Stite completeness theorem and reduce the problem of existence of omega model to consistency of certain proof systems. And now a proof theorist is really happy. He can do what he is best at, namely ordinal analysis. And we did a two-step ordinal analysis, but first it's just towards what ordinal analysis is. So it's actually about showing that certain formal theory, like some arithmetical theory or set theory, is consistent. So what you do, you have to find a proof system, often not really useful for, say, practical purposes, because it might be an infinitary proof system. But then you show that you embed your theory into such a formal system, and this you show that, say, everything that you can prove, like with normal logical rules, say in piano arithmetic, you can prove in certain infinitary proof system with omega rule. This omega rule makes a proof an infinite objects, but the reason why we work such a system is that then you can eliminate cut. In any like sequence style proof system, we have like rules, introduction of conjunction, of disjunction, quantifiers. And these rules have this feature that you introduce formulas that are more somehow built from formulas that occur earlier in your proof. Whereas cut rule is you get some conclusion from a premise that disappears later. And the normal procedure in ordinal analysis, well, we want to prove that this proof system is consistent, so we want to eliminate the cut. Because if you have, suppose that you have a proof of contradiction, which is simply an empty sequence. If you can prove an empty sequence in some sequence calculus, and you prove the contradiction. And the cut rule is the only rule that can give you this empty sequence. Because all other rules have something, some formula that they introduce. And cut rule actually cancels some formula. So we would like to show that having a proof in some proof system where we have the normal cut rule, which basically corresponds to modern exponents, can be transformed into a different proof, possibly much larger, but without cut rule. And the whole business in ordinal analysis is to eliminate the cut. And in case of piano arithmetic, if you eliminate one cut, then you get a proof larger by, well, the bound on the increasing proof height is measured by ordinal exponentiation. Whereas in predicative theories have ordinal bounds expressed in terms of collapsing functions. So going back to our results, we have two steps. The first step, predicative part, is due to occurrence ATR0 in our theory, and it involves this cut elimination with bounds expressed in terms of Veblen functions.
And then we got in predicative part due to the parameter-free pi11 comprehension, and then we had to use the technique of collapsing. So intuitively we collapse uncountable proofs into countable ones with proof height below this capital omega. Thank you very much.
Now it's time for questions. Questions?
So it seems to me that later proved the stronger statements to just basic picture. It seems to me it was about better quasi.
But it was used.
I think better work with so deep analysis.
I think so.
Yeah. Okay, so the statement was slightly stronger.
I'm quite sure that like the Freises conjecture is this statement, but like there is this close related theory of better quasi orders.
Yes.
And
Did you analyze it?
yes, but I'm not sure about exact applications of Freises conjecture there. But yeah, better quasi orders are it's another theory that gives lots of examples of theorems that gives us this this kind of work and examples of improbability. Nash-Williams theorem is it's the most famous. Yeah, and so by I mentioned I think that in this one of this series of partial interpretativity introduced by Kausler is a new bound of Nash-Williams theorem. I think. Right, so as far as I remember, like the original proof of Laver's theorem was through this minimal bit array lemma. But that one is known to, I think, imply pi11 comprehension. And
Can you go back to your theorem? The main theorem.
somewhere in the middle.
How does this relate to Freises theorem?
So this theory pi11 gamma is the best known upper bound of the string.
I see.
So Freises conjecture is provable in this theory. And before it was known that it is provable in pi11 comprehension. So it might be equivalent to this theory, it still might be equivalent to ATR0, but this is an open problem for many, many years, 30. So this is like one can say, more combinatorial upper bound in the string. And this also allows to maybe not compare yet because we don't know the precise strength of Freises conjecture, but there are analogous results, say, about Kraskow's theorem. So I think that there is a well-ordering principle that is equivalent to some formulation of Kraskow's theorem. And, yeah.
Are there any other comments, remarks, questions? If not, let's find the speaker again. And we have a short break, about 10 minutes. Też byś wyświetlił numer telefonu.
O, nie jest zapisane. Muszę od nowa wpisać te rzeczy. Jak to? Bo to na OneDrive było.
Dobra, to podaj swój numer telefonu.
515
515
400 642.
Jeszcze plus 48.
cena do przelania
170.
Nie, co ja mówię? 170. To jest dotacja.
Ile euro? 40 euro i 45 dolarów. 45 dolarów. I miejsce frasków pianka? Tak? Tak.
Ja bym to sprawdził, bo
Czekaj, a to nie miało być Aha, to jest nie.
tak.
Ja to znalazłem przed sekundą. To jest... Gdzie to
Właśnie można...
19:30 dzisiaj. Tak, prosiliśmy ludzi o wpisywanie się.
Ale teraz bardzo
Farina.
problemem otwartym, że gdzie jest udowodnienie 3 z tego co pamiętam, antyfroński balans to było przez tyle problemów. A teraz te 3 szlaki antydyskryminy porządku. No bo jak robisz na współskładu.
Aha, okej.
A teraz mamy w tym oszacowaniu, że pojawi się coś, co się nazywa delta 02, delta i po prostu mówimy, że nie tam każda bariera, tylko każda delta 02.
Jest nieważne.
Znaczy tak, no, że tak, nie są te bariery, które jakby istnieją potem, ale też delta 02 jest.
Bardzo dobrze.
On tam się przeniósł z Darmstadt. Wcześniej zrobił dokumentu. No, mi się raczej nie nadzieję, że Anton był jego znakomitym autorem.
Ja też.
Cieszę się.
Yes, yes.
Raz, dwa, trzy. Okej.
Jeszcze z jutro wieczorem mamy jeszcze bardzo. Może nie pozbierać.
Nie masz tego, nie masz afiliacji slajdów. A gdzieś tu są te twoje slajdy?
Nie wiem, nie wysłałem.
Trzeba
Platforma, ale wysłałem.
technicznie go poprosić o tego. Jeszcze chwila.
Ale dzisiaj trochę macie a o której
Tak, wydaje mi się, że było dobrze.
A gdzie grupą pisze, każdy tam oddzielnie?
To jeszcze powiemy, bo sądy grupa szmatu.
Wydaje się, że ma w dzień padać, a potem wieczorem już nie.
Ale stąd bezpośrednio o 6 się połączyły.
Już jestem przystan. Okej, to odpalisz, tak? Tak. Potrzebowałem po prostu kawy, inaczej by nie funkcjonował. To mieszkanie. Dobra. Okej, wyświetla się. Chce pan
Potrzebujesz mikrofon?
właśnie, jaki mikrofon? Czy
Nagłośnienie?
taki nałożeniowy, czy taki do ręki? Dobra, to już nie wiem, który był ten działający. Ten działający, czy...
To jest ten dobrze działający.
Okej. No to wiadomo, laser, to co do tyłu.
No tutaj będzie lepiej. Trzeba to włączyć. The next speaker is Tomasz Kania, which will talk about canonical reconstructions and forcing absoluteness of standard.
Thank you very much. Apologize for slightly vague title where standardness is not a mathematical notion in my talk, but nonetheless I'll try to explain what I mean by this. So the very motivational question was posed on MapOverflow, and I'm kind of a key user of it, so it caught my eye. And the question was phrased for groups specifically. But the results we're going to discuss today will go far beyond groups. But I think that for groups it's particularly interesting. So suppose you have two transitive models of set theory, one sitting in another, and suppose that you have a group that lives in both and tends to be or maybe make this let me phrase in a different way. So suppose without let's say two particular transitive models. So suppose you have a group that fails to be isomorphic to a group of all bijections on an infinite set, and can we force it actually to be one?
So is X fixed or?
No, that's the point. That's the point. So we are just asking about the very nature of the group, but we leave some room for the n-line set. So we can talk about abstract isomorphism class of a symmetric group without really a reference to a set, and for any other mathematical objects that we will touch upon. So more generally, let's say you have a class of objects that are, let's say, indexed by set. And well, let's for the sake of this presentation, let's call that like standard forms of some structure now. Like I don't know, in function analysis, that would be the space of all bounded functions given infinity over a set. So the more general question could be, well, is membership in this class preserved across transitive models of ZF or ZFC? And actually we'll see that sometimes the choice, well, the axiom of choice will be important for the sake of the argument. So, well, more formally, let's say this predicate that your object of interest is isomorphic to to a creature like this, some f of x with some x, to, well, let's say for a moment you can fix or interpret f as a symmetric group on a set. Well, it's kind of the first limit like sigma 1, 2, because you need to also express the existence of the isomorphism to a given f of x type object. So the question really is when or whether this can be defined in a phi-1 way, because well, getting rid of the let's say existence of the isomorphism will be a question really. So let's say this is like a heuristic rule for ruling out a phi-1 definition. So if you want to refute a statement like that, well, you need to find an object that is scientific class of interest in the ground model, and kind of force kind of inside the class. So, well, let's make a meta observation that, well, you can call a standard form. So think of the symmetric group or something, or an infinity over a set, like canonically reconstructible. If for any index set, if the index set can be recovered, let's say up to suitably definable by ejection from the abstract structure by a formula that in the, let's say, relevant signature. So for symmetric groups, the question would be, well, can you define what a symmetric group is without really saying that you need a set on which those bijections really live? Yeah. So, well, we could kind of phrase it using the slogan that if let's say the index of the standard in this sense, structure can be reconstructed canonically from the structure, then, well, we can think of this predicate as kind of downwards absolute from, well, forcing is irrelevant here. It's just an inclusion of transitive moments, but let's think of it, well, in this way. So is it downwards absolute? So for the class of symmetric groups, well, we will actually reach a strong conclusion that the fullness is actually pi-1 that is uniform over all ZF models. Okay, so the main, maybe not main, but main for the sake of this talk, kind of motivational result, would be this. So
What's fullness?
like full symmetric group.
This just is.
Yeah. So let's say, suppose we have two transitive models of ZF. So for this example, actually choice is irrelevant. And suppose we have a group that lives in the smaller model. So if you can see G as a symmetric group in a bigger model, then you can also see it as a symmetric group in a smaller model. Okay, so you can't really use forcing to destroy that. So no forcing extension, the ground model can let's say make a non-symmetric group into like a fully symmetric group. And actually, we will see that this is a pi-1 definition of the transitive models of ZF. And what is kind of interesting is that the proof actually gives you a mechanism that you can reuse for other classes of objects, but somehow it is difficult to distill this common feature. So pretty much for any, let's say, class of objects that I was interested in, I have to kind of redo the proof. Maybe there is a mechanism that will tell me when I can do it, but I need to repeat the proof for infinity, for C0, and other objects defined on sets. So I will not maybe read the complete list. I will maybe focus on the one that I enjoy the most. So we will see actually a sketch of the proof for the symmetric case, but actually the same theorem will hold for other objects like the full transformation moment on a given set, like the Taylor set Boolean algebra, the family of all relations on a given set. What else? Products of suitable rings, but of course you need to, the ring itself cannot be overly logical. So let's say for finally generated centrally decomposable rings, like familiar rings like Z, like the finite rings Zn at infinity and C0, and so the space of bandwidth and functions that converge to zero. The space of operators in a Hilbert space, and L1 interpreted as a Banach lattice. This is an interesting example because the language you use actually sometimes will make a difference in the case where the choice is needed or not. Because L1, the space above, it's an absolutely convergent of functions. With some of the functions, sorry, absolutely some of the functions is a Banach space, but it is also a Banach lattice, or there is an obvious order, pointwise order, that you can impose. And if you interpret this as you will see a lattice, choice will be irrelevant, but if you interpret it as only as a Banach space, actually we'll need the excellent choice to recover what we see in the extended model as a Banach space. So this is the list of, let's say, bad guys that require choice. The first one is slightly artificial, but it's artificial for a good reason. Namely, we have this characterization of axiom of choice using, let's say, choice families on two element sets. So if you kind of consider equivalence relations that kind of take into account only what happens in the first ordinate and we kind of ignore the second ordinate, but the set of possible values is finite, like at least two. Well, you can intuitively think of the situation with the need of a choice function and a family of doublings that is actually equivalent to C. So actually, we will see that that this thing requires choice. What else? The space, the null space of finitely supported functions. The most, I think, important example is the space L1, interpreted as a Banach space, not as a Banach lattice, and L2, Hilbert space. So here the issue would be the existence of a basis that requires some amount of choice to be proved, and we will see that this is the very reason why we need choice. So we can kind of informally kind of phrase these two situations that, let's say, in the former class of objects, we have something like ZF descent, where we can descend to from a smaller model maybe to a smaller model. I'm not sure if it's phrasing is perfect. And likewise, ZFC descents where choice is required. So let me repeat this instruction that, well, you can have a family of two-element sets and Daltons without a choice function to produce something that I will call a sign torsor. So torsor is a term borrowed from algebraic geometry, something like a principal bundle, from which you like to recover the object but without the choice function, you would have hard time actually doing so. So occasionally I would use the word torsor for principal function of things. Okay, so it was maybe not a really short introduction, but let's try to be a bit more formal. I'm not sure if we will actually see all the details, but at least for groups, it is good to see the proof. So the setup in this talk is that we fix to a path of transitive moments of ZF or ZFC. That of course are to agree on the membership relation. And of course you can think of the bigger one as a forcing extension, but it is completely irrelevant for the sake of the argument. So it's just a pair of transitive models. And let us kind of write F as a set for this kind of standard, vaguely defined standard object that you define over a set, like the symmetric group. And let us use this superscripts N and N in order to highlight that we can do this in one of the models, N or N. So, well, typically we'll have an inclusion. However, well, because the outer model may add new subsets, sequences, whatever. And here is also an important convention that for structures that are defined over, let's say, real or complex numbers, we need to make sure that these structures actually are the same in both models. So kind of tacitly we will be kind of assuming that kind of real numbers or complex numbers are the same. So this applies to all those finite space related structures. Okay, so well, we could kind of appeal to solvedness. So we can actually see the transitivity. You can see Fm computed, well, F computed in F as the intersection. So that's not really a problem. The question would be whether you can actually describe it the other way around. So maybe let me highlight the case of compact operators in a Hilbert space. Here we're actually using the fact that compact operators in Hilbert space arise as limits of finite rank operators. So let's say an old operator where that is seen by let's say the bigger model as compact, well, satisfies this kind of compactness, or let's say finite dimensional approximation. So you can approximate it with finite rank operator. So in that case, you can also see this happening in the smaller model. So it also arrives at finite ranks. That's why we can also we also had a situation where the compacts are interpreted as compacts. So, well, let's say we have two transit models, and what about the isomorphism to or onto a set or onto, let's say, a set in this standard class. So let's assume that we have this nice descent. So, well, if you can interpret your object as a standard object in N, well, then you can interpret it as a standard object in F, in N objects. The reason is that the isomorphism axioms, this is sketch again, are delta 0 in the parameters and the operations that are kind of relevant to your I don't want to say category, but to your object. So they are absolute between the transit models. And appealing to transitivity, well, if, let's say, the value of theta is in M, well, you can also see that because theta is in M, well, you have this value belonging to M of M, and so on. You can actually verify these things. It's indeed a morphism. It is indeed injective, and it is surjective and here happy. So this is actually quite elementary. Okay, and let's observe that we have the following high-level one definition test. That if you have a class of to be standard definable objects that are definable uniformly as the ZF models by a formula of this form, where phi is absolute, like delta zero or something, then actually this class is downwards absolute. In this sense, yes, that if you can interpret this in N, you can also do it in N. Okay, so the usual strategy for, let's say, the usual strategy will take an object that is in M, but it's not witnessed, but it's not really in the standard class when read in M. But you want to be in an extension. It's a possible route for disproving a high-level one definition. So what we will show that in this ZF catalog of objects, this strategy varies badly, and especially for groups, for symmetric groups, it will be clearly seen that this is a pilot one definition. Yeah. Okay. So now a little bit of elementary group theory from group theory 101. That, well, we would like to interpret transpositions. So that mix two elements. So let's note that we have a very elementary characterization of, or maybe a definition of a transposition. So what is a transposition? Well, let's say the following formula: we have an element that is not the unit, but let's say it is, well, square, well, x squared is equal to 1, and for all g you have this order 6 how to call it, well, this condition that for any element y you have this, well, and this defines the set of transpositions. And why is that? Because, well, all these conjugations range over the full conjugacy class of x. So, like for definition, so the formula says that if x is a non-trivial inclusion, and let's say you multiply x with any of the conjugates, then it has order divisible. Well, that divides 6. So if you have a conjugate that, let's say, mixes C and D, so we only have the following 3 cases depending on the relation between A, B, and C, D. So you can have order 1. It will have order 2 if the support set is joint, and order 3 if they share one point. So in each case, we have divisibility. Well, it divides 6. Therefore, the order, well, the 6th power is 1. So this formula will hold. So now, well, you could prove the converse. I'm not sure if we have time for this, but it's a group theory exercise, effectively, to show that this indeed characterizes transpositions. So we may actually think of transpositions regardless of the elements of the mixer. It's a purely group theoretic definition.
that quantifies over the group. For all y, you have this condition of the sixth power. So I will spare you this second slide in group theory, but good news is that we have this. Well, we can relieve, but we can get rid of talking about elements, particular elements of the set, but we have a purely group theory definition. So now the idea how to reconstruct the symmetric group would be, of course, to appeal somehow to transpositions that are ubiquitous. So for a non-commuting, let's say, elements, well, we can define the star to be this set of all, let's say, elements in R, so that we have this anti-commutation. So RS is not SR, RT is not TR, and likewise, well, R is not STS. So here's the thing, that if you have elements A, B, and C, so that all A, B, and C are different, then, well, and you multiply STS, so that it becomes a transposition of B and C. And you have another transposition that fails to commute both with S and T. Well, what you get is that it has to mix A and D. So we have a clearer description of the star in terms of the transpositions, where we can actually arrange all the D only. Yeah, so you can express them in this way. So this is like one parameter definition. So you could call it like the avatar of the underlying set. So the map that assigns A to the relevant star, it's a bijection. I mean, we can check it, but it's a bijection. So what we can do is this: how to let's say see that we'll get some symmetric group. Okay, so Y. So what is once again, this is the set Y. We consider this set of stars, really. Yeah. So now what we can define a map from G to the symmetric group in M of the set of stars in the following way. So that we take we just consider the conjugacy classes. So conjugation by an element G, well, it preserves transposition, it preserves non-commutation, it preserves everything. So it only permutes the stars. So in N, under the, let's say, if once we assume that we have an isomorphism, we kind of have like a natural action of the symmetric group on, or X, on the set of stars. And this is kind of tautological that you have it in N. So now once you apply the sampler map applied to the symmetric groups, so you see that actually theta gives us an isomorphism to a symmetric group in the smaller model on this set of stars that may be or may not be the same. So let's maybe recapitulate the proof. So that so what do? We have like a definable, or we have like a definable copy of the set of all transpositions. We have definable family of ordered pairs. We have definable membership in the star, and we define the underlying set Y using the star. So we have like a definable quotient that replaces the set X in the first order signature, and everything is achieved by conjugation. So this actually gives rise to a pi 1 definition. How much time do we have?
16.
16. Okay. Okay. So without maybe delving into details, well, we have, or we will see in the next slide, clearly the definition, or maybe this slide should we read it, that we have a faithfulness expressed in this kind of tautological action, and as well as surjectivity. So this formula is first order. Of course, we just quantify it over the G. As a single universal, let's say second order quantifier for R. So it is pi 1. However, there is one tricky point, namely, in order to make it work, your set has to be big enough. Where by big enough, I mean to be at least 8 element set for certain computational reasons. But of course, it is not a problem to keep it kind of fixed, or look at the calculation tables for small symmetric groups. But we need to kind of exclude or include it, and if you prefer, so that to be completely correct. The class of groups that are isomorphic to symmetric groups is defined out of such a formula. So either you are isomorphic to S1, S2, S7, or you satisfy the formula from the previous slide. Okay, I think I've already said this. I will maybe skip these remarks because we have more classes of objects, at least to skim through. For transformation monoids, it's a similar game. This class is also, well, you can also, we also have the set for the set of transformation monoids. I will maybe spare the details. What is maybe a bit easier are, let's say, complete atomic Boolean algebras, namely palisades. So this class is also that down with absolute, and for that reason, well, we have the result also for them. And we can actually see more or less what is the kind of new, or maybe the new presentation of the round set. Well, we just say, well, we look at those ideals, so via the SOMA. This is the identification we want to use. So from that reason, we are that absolute values solutions are complete atomic Boolean algebras. Also known as palisades. But what is maybe really interesting here, that completeness alone is not canonically reconstructible. You can destroy it. So here, atomicity is the necessary ingredient. But it's so because it gives you access to this index set, the set of atoms that you mark into ideals, and you have it. Without this, you can destroy it. Relation algebras are not that surprising because these are just palisades on the squares. Full-blown, so like all operations in a world, finite arity operations. There's also maybe another interesting and not surprising once we have seen the proof for the palisades. So let me maybe move to something at least to be more interesting, to product rings. So, and maybe we'll see why we need finite generation. So suppose we have a ring that is finitely generated, and I want to exclude central idempotents besides the triggered ones. So we can express a formula that you are isomorphic to product ring, and actually this relation is downwards absolute. And here the idea is also to go through the power set algebra. More or less the idea is that when we look at the atoms of the central atom, we think of the central atoms as atoms. So we recover the power set of it. So for each and we, let's say, map elements to let's say, a constant function in the problem. This is not a problem at all. And let's say for every central idempotent, we interpret this as a projection, like a coordinate projection map in the product. So this is all kind of well-defined modular of the ring itself. So in that case, you can. So this is what is it really morally saying that you can use kind of the good projections, good idempotents in your rings to first of all to kind of like subdivide the original ring into kind of orthogonal pieces using the so-called Pearson composition. And then with that pieces, when you look at the ring that you suspect is isomorphic to the product ring, you can kind of interpret the coordinates of the product ring. Hence, you have a product ring in your small model. More or less, this is the idea, and non-central idempotents kind of mess up. Okay, and for me, I think this is the most interesting, maybe not the most interesting is the one, but the second most interesting example is an infinity in points. C0, these are Z downwards absolute, remember about the scalar dimension. And what is the reduction again? Well, in L infinity, we have, and likewise in C0, we have those vectors that will standard unit vectors of zeros and with one in one particular place. So these are the minimal idempotents. And what we do, we recover this set of minimal idempotents. So abstractly, once you have a C-star algebra that we suspect to be L infinity, well, you look at the set of minimal idempotents in it, and then using actually this is quite similar to the product ring case. You define these corners, and well, because of minimality, you have a number associated to the minimal to the rank 1 projection really, and this number actually recovers the structure of either infinity or C0. And it's interesting, and again, this is the atomicity that plays the crucial part, because it's not like saying, oh, I know that a commutative C-star algebra is a CFK space like Elton-Reinhardt, and we're happy, because, well, you can kind of destroy the properties of the spectrum by going through across models. So it is the atoms that keep everything kind of intact. So yeah, this very similar idea, let's say, for endomorphism rings, but I will spare this in order to see when and how actually we made the choice. Or maybe before that, let's see also the compact operators and band operators. So what is really the reconstruction theme? What is the underlying set? Again, we go through minimal projections. So these are to be the rank 1 operators in BRH interpreted. So using that, we kind of define like a pre-Hilbert space, and kind of completeness will become automatic, and maybe it's too condensed, but I just want to highlight that the idea is exactly the same. In this case, we look at minimal as opposed to the rank 1 projection thing. And for complex, well, we've seen that we have to descend by the very nature of complex operators as being approximable by finite rank operators. Kind of the same idea applies to these structures. And L1 as a Banach lattice. So I think my presentation is the last case where you don't really need choice. So what is the set that we use for reconstruction? That's the code. Yes. So let's take the elements, the non-negative elements. The kind of the positive part of the units there. And yeah, so that it has this property that if you add something, so like extreme points, of the ball, and in L1 we kind of know what they are, like plus minus the scalars. So what we do, well, you can define like a gauge map that tells you, well, how far you need to go in order to be below an element from this positive code. So this map, actually, you can use this map as an exercise to define lattice isometry. So this kind of lattice order gives you a set of effectively at extreme points as the set that you recover. So it's like a sine torsor because it's either plus or minus in the real case. We're working with the real scales. And this is the place that breaks down for just Banach space isomorphisms that may be more complicated. Okay, so let me, before we delve into that, let me mention the slightly artificial, but I think illustrative example of where the finite covers. So, well, we just identified the two elements if they have the same first coordinate. So this class is downwards absolute across transitive ZFC models. And because in ZFC, well, you can choose kind of these bijections uniformly using the axiom of choice, and we are happy. But in the absence of choice, well, not quite, because it's pretty much equivalent to having a choice function on an infinite family of, let's say, n element sets, which you can't really afford without choice. Okay, so yeah, that's the abstraction. But as long as you have access to a choice function, well, everything goes well, which means that assuming that such a choice function exists, or let's say you can, let me phrase it in the opposite way, that this class Cn has no pi11 definition across transitive ZF models. So this is a very clean example, kind of artificially manufactured, but it shows why when actually choice may matter. And this example, if we think, is kind of in essence quite similar to the L1 situation, when L1 is regarded as a Banach space only, Actually, this is and was absolute once we had ZFC. Why? Well, the set of extreme points of the ball is definable, and we know what the extreme points are, plus minus, in the real case, plus minus the standard unit vectors. In the complex case, you have just, well, points from the circle, really. So we have an action of the torus, and the set Y is just the set of extreme points where we are kind of identifying the complex sign. And why we need choice? Because in ZFC, well, you can choose kind of like sections in this bundle, so that you can provide a unique scalar that minimizes the distance. This now you can actually do the proof, but such a section need not exist just in the some amount of choice is required. So this let's say, let me call it this complex sign torsor, when you see it exist, but without choice you can't really conclude that yes, this is what I want. Yes, so for in order to see that, well, let's I'm not sure if I will find those sets. Yeah, maybe this is too dense. Maybe let me comment on the conclusion. So you kind of, when you do it in ZF, you see that you have constructed something like a direct sum in the L1 sense of certain pieces, but you can't really conclude well. But you can't really conclude that it's the same as the space of finitely supported vectors on any underlying set, because in order to do that, you need a choice function, or you would have provided a choice function this way. So you kind of see it around the corner, but you can't really touch it in ZF. That's the kind of illustrative way of saying this. I will speed up a little bit. And for hybrid spaces, L2, it's exactly the same situation where you can't see the basis, therefore you don't know whether it is L2. And I think I will stop here with some questions. So thank you very much.
Thank you very much for your talk. Your questions, remarks, suggestions? I don't see any, so that's fine. Okay.
Thank you very much.
All right, I have an announcement before we go on the break. There is still about 20 persons who didn't decide whether or not they vote for the conference dinner. Before you go to the break, reach Agnieszka, please, and answer if you are going there or not. Please decide. And now we have a 2 hours lunch break. And you can go on your own. If you don't know where to go, you can again reach Agnieszka, and she will take you to the guide to the Successia, where there's some restaurants and fast food as well. All right, so we see here you go. Excuse me, everyone. There was a mistake on the slides. The banquet is today, not tomorrow. The conference dinner is today at 7:30. There is a mistake on the previous slide. So that's why we are asking for deciding today, because we have to tell the restaurant how many people will be. So,
Okej, dobra.
Mamy w końcu chwilę dla ciebie.
Okej,
Dobra, sekunda.
Powiedzcie mi, teraz wy macie...
Niestety nie, ale
No co najmniej dwa. Tak. Będzie dużo wstęp, będzie
nie trzeba.
To będzie intuicyjnie, z jednym z jakimś uczniów starszym tematem.
To nie jak moje dowody. Znaczy, zdarzyło wszystko, co trudne dla tematu.
Lewa decyzja.
Wiesz, ja się musiałem zapomnieć, że hipoteza kontinuumowa co no tak, ale ja niestety przeprowadzuje pozornie łatwe sposoby.
Jak mój szanowny promotor, który też mi mówił, że to akurat jak pisze jest...
Jest drugiego bez drugiego. Tam jest taki pomimo szkolenia Hacker, kojarzysz? Ona tam biega na baterię do kafinego. On był tam, jest Iowa, też mówi, że nie ma nic dla tego gościa, ale że jest fajny, więc jest nawet sterowany. Czy on ma, on się nazywa Andrew Baxter, więc coś tam
jest, nie?
więc jakiś chyba, nie mówi po polsku, ale ma przynajmniej korzenie.
No ale nie mam możliwości, nie
Co jest
to dotychczas świetnego. On 100 razy dużo współpracuje w publikacjach, z tym teraz trochę takimi rzeczami jak
Właśnie sobie uświadomiłem, że kurtki nie ma. Tutaj zostało.
Te ciała z tym Saturday. Ale było parę wpadek.
Tak, znaczy rzeczywiście to coś, czego ja nie przewidziałem. Znaczy, no, po prostu nie. To jest to, że jak wchodzisz na stronę konferencji, to tutaj jest jedno, a mapka jest nisko. Teraz już dopisałem.
Za 15-14. Będziemy musieli tam, jeżeli chodzi o Fundację Politechniki Łódzkiej, to mamy między innymi zrobić zdjęcie welcome tego slajdu i tam na tym slajdzie powinna być informacja, że to było wsparcie, że było wsparte finansowo, więc zrobimy jakiegoś slajda i go tutaj tak musimy zrobić jakiś tam, pomalować trawę na zielono, żeby może zamknę, tak się nie powinno robić, to jest nawet informacja, że
wiem, ale nie było innego wyjścia, nie? Można teraz wywietrzyć, bo na zewnątrz jest chłodno cały czas. Ja bym właściwie podniósł te rolety i otworzył okna. Czy masz coś przeciwko?
Żeby się dobrze zwijały. Potem nie było, że coś żeśmy tu popsuli. Uważasz, że tu jest za chłodno?
Nie, właśnie, że zaraz może być troszkę za ciepło. Ja bym podniósł rolety i przewietrzył to dopiero jak można.
A, jasne. Tam jest opcja podniesienia rolet do połowy.
Jest opcja?
Tak, trzeba tylko, jest opcja zatrzymać. Robisz stop. Może zrób stop, już będzie prawie.
Dobra. No tu.
Stop. To Bartosz to odkrył.
No dobra, teraz tak.
Ja się nigdzie nie wybieram, więc ja tu będę pilnował tego.
Dobra, w szczególności będziesz szedł do naszego pokoju?
Nie, będę pilnował tego.
Dobrze. To ja połączę się z Beniakowem, bo on prosił, żeby zrobić testowe połączenie.
Okay.
i potem pójdę się zdrzemnąć.
Michał padł na skorzystałem z swojego bacza w toalecie. No, to jest nie dzwonił. Agnieszka do mnie dzwoniła. Co może
Przed chwilą?
10 minut temu. Dzwonię do mnie. Czy ktoś dzisiaj dojedzie jeszcze? Czy są szanse, że ktoś spośród tych, co są, dojedzie i może być na tym? Ma Sabo?
Saboka dzisiaj nie będzie na pewno.
Może masz jakieś...
Ty masz laptopa tutaj swojego?
Nie.
Czy to słychać, jak ja tu mówię coś? No niby słychać. Zrobimy inaczej. Ja zaraz wyjdę. Spróbuj coś poopowiadać tutaj, jak ja wyjdę, dobra?
Ale coś mówisz, tak?
Tak. Nie, stąd. Z okolic pulpitu.
Jakoś się połączyłeś z tym gościem?
Nie. Ale dostał link.
To co, będziemy testowali, czy mikrofon działa?
Tak.
Okej. Dobra. Raz. Ja cię nie słyszę inaczej niż z korytarza. A ty mnie słyszysz z laptopa? Dobra, tu nie słyszę z korytarza. Wiesz co, nie słyszę, więc nie wiem, co mi mówisz. Słyszę tylko, że coś mówisz.
Głośnik, tam masz 3 do wyboru, widzisz?
Aha, mam zmienić.
Tak.
Zakładam, że coś mówisz, ale nie słyszę. Przełączę na drugi. To może teraz coś powiedz.
Załóżmy, że KSY jest liczbą porządkową.
Teraz słychać.
Głośników?
Tak, słychać. Trzeba włączyć na Asus VGA 23A. Słychać z głośników.
Dobra. Nawet nie ma sprzężenia.
Nie ma sprzężenia, bo masz opóźnienie.
Dobrze. Dobra. A teraz tak, ja się muszę zdrzemnąć. Spałem dzisiaj niecałe 6 godzin i to jest...
Dobra.
To ja pójdę do siebie. Tutaj...
Ktoś tu się pojawił. A, JI to jesteś ty.
Tak. Tutaj jest szansa, że się pojawi Ben Jakow, że prosi, żeby go wpuścić.
Dobra.
To wtedy go wpuść i no zobacz, czy może udostępnić slajdy, czy to dobrze widać, tak? Czy on słyszy ciebie, czy ty słyszysz jego.
Będę gdzieś się tu przechadzał, to...
tam?
Roku. Siedzę sobie, gram w szachy.
Spoko.
Na tym spojrzałem.
Jak tam, jak do tej pory? Wszystko ok? Wszystko tam...
Tak, wszystko ok.
No to dobrze.
Chcę tu zagrać. Cofam się. Przepraszam, jestem mało gadatliwy, bo jak gram w szachy, to...
Spokojnie, spokojnie, trzeba się skupić.
Właśnie.
Teraz o której kolejny wykład jest? Ewentualnie sprawdzę.
14:50.
A, spoko.
do wiadoma. Rzeczy są. Macie jak się składa? Męczę się, sam nie wiem czego chcę. Po to się znikam. Kubusie, bo tak, się chodzić z Kubusiem chyba. Bo tu nie ma Maciej. No to ten ekran jest nad wami. To sobie na wierzchu położyłem.
Nie, to jest na tarczycy.
Proszę?
Na tarczycy.
Kawkę włączyć. Już tam kawka jest.
Nie będę przeszkadzał, też sobie też do komputera.
na końcu tak się osłania. Ale wszystko jest bardzo dostępne. Tak, tak. Po prostu wszyscy wiedzą.
Pisałam temu gościowi dokładnie tak, że tyle mi napisałeś wege, tyle mi napisałeś mięsnych, napisałam i jakiś 7 pewnie nie zdecydował. I konstant. No ja no najwyżej zdejmę parametry. No bo też mówiąc o nie, bo powiemy tym, którzy przyjadą, że nie.
Informację, że ta konferencja jest finansowana fundacji. Trzeba mieć taki startowy slajd, jeszcze też zrobić zdjęcie przed tego zeszało.
Okej, to ja idę robić fotki. Bo tutaj robiłam.
Że będzie tam było przed kamerą, żeby było ciastka, robiliśmy walec, wrócić do ciastka można. Potem będziemy musieli szybko poprosić o pytanie, czy zgadzamy się na zdjęcia. Myślę, na takie skojarzenie.
Okej. A jeden działa. A może nam ma być tylko, że brzęczy jakoś. A można też... Krzysiek Kropiński mówił z tym, tak? Ale to, że kolejni już nie chcieli używać. Dobra, rozumiem. A slajdy? Nie. Obyt zaczęły
Mam wrażenie, że one, że z nich wchodzi w interakcję z tym wskaźnikiem.
A ze wskaźnikiem. Nie jest.
Dobra, troszeczkę można
zamienić, nie?
Ale zamienić. Nie jest to pointują.
Okej, spytamy się Piotra, może jeszcze czym chce używać, bo ten był najtrudniejszy, nie? Tylko tyle, że...
No właśnie, wyciąg jest.
Był, zniknął.
Okay. Bo to jeszcze...
Trzy jeszcze. Że tam zaklaskał? Może zaklaskał, żeby przechodzili.
Państwo ty teraz na UFU, tak?
Tak.
To jest przyjemność. No, tak.
Cześć.
Tam fajnie pracować.
No, nie narzekał, tam już robiło tylko przedłużenie. Z różnymi rzeczami.
Mikrofonu można.
No więc właśnie, wolisz bez mikrofonu.
No też, jak było cicho.
Znaczy jak głośno mówisz, jesteś przyzwyczajony, to jasne. Nie, tego tym bardziej.
Jak były protesty, to leży, tak?
Dobra,
tak, sam sobie to
Tam jest jeszcze ten pointer.
Właśnie pointer, a to może działa? A to sobie taki... Gdzie kieruje?
Słuchaj, właśnie, czekaj, no właśnie nie. Może czego?
Włączony. A to USB ma wstawcone. O, proszę. Okej. A sam pointer tu? Okej.
Jest.
Wielkimi literami można pisać na tablicy?
Można, tylko się skręta, ale
Nie no, każdy jest zawsze.
tutaj jest skręta. No ma przygotowana, jest zobacz.
A, w ten sposób. Dobrze.
Może ja ten pójdę już wykraszczę.
Coś się działo?
Nie ma nic.
Ale
Tak zetknąłem razem zegarek.
A jakie były Warszawy? Może prosimy po sobie
Ja teraz sobie wyłączysz sobie.
Kiedy to różnice, ale nie wiem, cały plan.
Ale tak, tak. Przez chłopnie można było tak, tak.
Okay, so welcome everybody. Okay, and our first speaker in the afternoon session is Piotr Kowalski from the University of Wrocław. He's going to talk about model theory of differential equations.
Thank you very much. I will speak without microphone. If it's too silent, tell me please that I will use microphone. Okay. Already silent? Joke. My sense of humor is. But it's a Polish joke, I will get it. So thanks a lot for the invitation. I think it's my second time in Lodz, and first time was somewhere at the end of 1980s, so I don't remember anything. So I'm very happy to be here again and see the city. Okay, so I will talk. So the talk will have two parts. The first part is a survey, short survey about model theory of differential fields with one derivation and characteristic 0 with some applications. And second part is about my joint work with Omar Leon Sanchez. Okay, so in fact it will be just about one example of something, but also for this example, so example is about two derivations, but somehow it makes more sense when you know the theory with respect to one derivation. So this introductory part has also kind of motivating reason for the second part. So I will start pretty slowly. What is a derivation? It's an additive function on a field satisfying Leibniz rule. So I focus on abstract derivations. We are used to derivations coming from analysis, but we can also consider them as abstract algebraic objects. So then a differential field is such an abstract algebraic object. It's a field with one extra unary function, which is a derivation. So obviously it has an obvious language, yes, in which we consider such structures, the language of rings, plus minus times 0, 1, with this additional unary function symbol. I don't see it yet, I think, but all of this is in first order logic, normal standard, classical first order logic. So examples like this, all of us know, if we start from a field, then if we take field of rational functions, it has this natural partial derivation on it. X goes to 1, x to the n goes to n, x to minus 1, and so on. It is 0 on the field. Similarly, on the field of Lorentz series. And for example, if we look at the field of meromorphic functions, so now it's something actual, now there are actual functions on some open domain with the usual derivation with respect to the z coordinate. Okay, so The specs part of my talk is about the theory, which is denoted this year 0, differentially closed fields of characteristic 0. So it may be defined as model companion of the theory of differential fields of characteristic 0. So I will explain what is it step by step. So it means that the class of models of this theory is exactly the class of existentially closed differential fields. So what are existentially closed differential fields? So it's like kind of algebraically closed. So it's a very general definition. A differential field is existentially closed if all possible solvable systems of differential equations with coefficients from this field already have solutions in K. And what do we mean by solvable? That in some extension it has a solution. So of course one should show existence because one can always define such a structure, such an existentially closed field, but it's not immediately obvious that the class of it is axiomatizable, is elementary. But in this case it is. So I think first time it was done. So proving that this class is elementary was done first time by Robinson, and then Bloom gave these elegant axioms. So we have, so it's enough to say, and actually, maybe I didn't say, but the systems, not necessarily in one variable, in any fixed finite number of variables, okay, that's the definition, but actually Bloom shows that it's enough to give axioms in one variable. Similarly as for algebraically closed fields, but for example, if you change derivation to automorphism, then you cannot give corresponding axioms with one variable. So it's something special. And then the axioms are like this, which is two differential polynomials. Maybe I say a bit. Yes, so differential polynomial, something like so it's a polynomial, but not only in the usual variable x, but also in variable x prime, x double prime, and so on, which represent iterating derivations. Okay? And then obviously the order, okay, so this is a differential polynomial of order 2, because this is the highest number of iteratives of derivation visible here. And then the axioms say if you have two such, one is non-constant, okay, and differential order of G is strictly less than this one of F, then you have this 0 of F, which is not 0 of G. So you know, it's supposed to say that we have always solutions, we have always differential zeros of the differential polynomials, but which are also kind of generic, which can avoid zeros of any polynomial, differential polynomial of a smaller order. Okay. So this is the set of full axioms. Differential is essentially closed, depending if it satisfies this. And this is obviously first order. It's not one axiom, but we can write it as a set of axioms, kind of indexed like by complexity of these differential polynomials. For each fixed complexity, you write all possible axioms like this, and then get infinitely many such, axiomatizing this theory. So this I'm trying to say that this is very general definition, which may be given in the case of arbitrary theory, replacing the theory of differential fields. It's convenient to add inductive For example, it means that it can be axiomatized by, for all there exist something quantified 3 axioms. Equivalently, union of chain of models is a model. So any inductive theory has existentially closed models, and here, existentially closed has the same definition when we just replace system of differential equations with quantifier formula. Because differential equations have no quantifiers, like this one, equals 0. So it's a observation that in the case of differential fields, you can reduce quantifier formulas to formulas of such form, and this is general definition. So then, as is a motivating example, the theory of algebraically closed fields is the model companion of the theory of fields. And so that's the main intuition here, motivating example. But from totally different kind of structures, the theory of dense inner orders without endpoints is the model companion of the theory of inner orders. Okay. So you have this formula saying something is in between, so you have to make it dense, but you have formula saying something on the left, something on the right, so it cannot have endpoints. And this is enough. Maybe more interestingly, you cannot do it for groups. The theory of groups, there are existentially closed groups. And they are studied, but they cannot be axiomatized. That requires little argument. Similarly, the theory of commutative rings has no model companion. One cannot axiomatize existentially closed commutative rings. Actually, nilpotent elements cause problems. The theory of reduced ones without nilpotent elements has model companion. So it's not obvious whether this exists or not. And sometimes it's a very difficult question whether a given theory has a model companion or not. Okay, so going back to TCF0. Some properties of this theory, which I already hinted. So it has quantifier elimination. So every definable set comes from differential equations. It's a Euler combination of solutions of differential equations. I will not define what it means, but it's omega stable of Morley rank omega, which you should think of, there is a well-behaved notion of rank of dimension, but sometimes it has ordinal infinite values. Like the whole universe has then Morley rank omega. Okay. I will talk a lot about strongly minimal definable sets. So those are like smallest possible infinite ones. So those are such definable set. Okay, in any you have definable set, we are thinking what can be its definable subsets. So always finite ones are there and cofinite, and strongly minimal are such that there is nothing else. Okay, so it cannot be definably split into 2 infinite subsets. So in particular, it has Morley rank 1 and Morley degree 1. And the first structural result, brought by Sokolovich, there is something which Dilbert predicted always happens, but it doesn't, but it happens here. So Dilbert's trichotomy holds, if we have such minimal set, okay, it can fall into 3 different families, which again, I will not define. First one is kind of geometrically trivial. The geometry of definable sets on products of such kind of comes only from some lines and diagonals. Or it is like group-like, actually like a vector space, or it's a field-like. The field is actually the field of constants of the derivations. So 3 different kinds, all of them are possible, but yes. there are criteria to say in which one does it fall. And this already had applications, but actually more in positive characteristic case. So this was used by Kruszowski for the proof of relative Mordell-Lang conjecture from affine geometry, where actually the main point was positive characteristic version. I will not talk about this. So those are the properties of this theory, structural properties. Okay. Hello. Now actually I'm focusing on one more notion of dimension. So let's pick a big differentially closed field. It's like sometimes we say we work in complex numbers, big algebraic closed field. So here something like this. And then, okay, notation for differential field generated by some set. Then we define, sometimes people say order, but let's say algebraic dimension of such a set as transcendence degree over this K, as transcendence degree of the differential field generated over K by this. So it may be finite or infinite. If you take just one constant element, it will be at most one. But if element is like differential transcendental, if this A is just singleton, it will be infinite. So this is like another notion of dimension. Then for define our set, its dimension just take maximum or supremum of dimensions of its elements. And then this is always greater than equal than Morley rank. But there is an interesting result that one of them is finite. So if Morley rank is finite, then actually this dimension is also finite. So it may be bigger, but cannot jump from finite to infinite. Okay, and this is something actually the point of the example will be that in case of two derivations, the second is not true. So let's see some examples, and actually there are some recent results that some famous differential equations give model theoretically interesting examples. So first, in general, if we take, there is a little mistake here I noticed on the train I didn't correct. So this polynomial should have something in the y coordinate. If it's only about x, we get finite set. Here I should say not just here. As otherwise it will be dimension 0. Okay, so if we take a reducible polynomial in two variables and make from this obvious differential equation, it defines from the minimal set of the algebraic dimension 1. Okay, and then Poisson, maybe that was the first non-trivial example. Poisson proved that such a set, which is now of dimension 2, yes, it is order 2 differential polynomial, is still strongly minimal. And then Ronnie-Naglu and Anand Pillai started to look at classical equations, which were analyzed by several people, which they refer to as Japanese school. And actually, these people kind of showed strong minimality, but in different terms. And then Naglu and Pillai put these results together and proved in general that, so there are 6 families of this span level equation. I just wrote 2. Sometimes they have some parameters. If these parameters are generic, like algebraic independent, then one obtains strongly minimal sets defined by these differential equations. Now, very nice formula. Okay, Okay, so I may say, what is it if somebody asks, but there is something called J function coming from J invariance of elliptic curves. And this function satisfies this differential equation, which has some general Schwarzian form. And they showed, right, against Scanlon, that this is, again, strongly minimal. Now it is of dimension of order 3. Okay, and then Lask-Sams, Kazal, Freitag, and Naglu showed strong minimality of a very, very large class of equations, including this one coming from some automorphic functions. On the other hand, Remy showed strong minimality of kind of almost all possible order 2 equations. I finish at 25 or 35? So now another application, which is quite interesting. Sorry, this is. So I said before that the strongly minimal sets fall in 3 different categories, and I didn't define them. So I will focus on those which are trivial. Okay, so let's look at a very simple equation. We just say that derivation on x is some rational function of x. So it fits in this text. Example. The reducible polynomial is just y minus something. Okay, so we look at such equations. So maybe geometrically we have just affine line. And here we have derivation and also this rational function polynomial, and we look at the set of those which are the same. So it's always strongly minimal, but then actually it can be fit-like or trivial. So Truszowski and Japanese mathematician Itai gave a criterion that it is not geometric trivial, so coming from the field, if and only if inverse of this function has no simple poles. Simple pole is a pole of order 1, so like 1 over x, but not 1 over x squared. Or all the poles are simple, and then the residue is the parameter edit. So there may be several simple poles. So they all should be rational multiples of each other. Okay, so that's the criterion. And then it can be checked. It can be checked even in the simpler case when our function is a polynomial. So if one is able to decompose 1 over f into simple fractions, we have 1 over everybody should be able to do it. And then actually it satisfies this criterion. The question mark over question mark is a rational number. So it's not geometrically trivial. Even easier, of course, if the degree is 1 or 2. But then if you go to degree 3 and take non-zero C, if you try to do the same, then the ratio will be third root of unity. So it does not satisfy the criterion, and it gives like the simplest example of geometrically trivial set, And this is the example I will talk about in the case of derivations. So I want to point out here that somehow this is like a simplest example of some interesting differential equation from model theoretical point of view. So the name may be confusing, but trivial ones are actually interesting. That's what really happens. Just the name is, the geometry is trivial, but they are mysterious and interesting. Okay. So application also of triviality. I guess all of us heard term classical function, but it's never properly defined. Yes, so it can be defined in several ways, but let's say that we start from some known or a known function. So we start from functions like rational function, and then let's take algebraic closure of it. So we allow square root, cube root, etc. But we also can take, we can integrate them. So we can take antiderivative or anti-logarithmic derivative. If f is classical, g prime over g, this is logarithmic derivative is f, then maybe nobody can see, but then g is also classical. By definition, that's what I mean in the last, by this logarithmic integration. And also some other kinds of integration of this form. Okay, so classical functions are obtained by some inductive process using these steps. And then actually, Paul Level in the 19th century was interested in differential equations, which he called irreducible. So there are such differential equations whose solutions are never classical. All the solutions are strange and somehow cannot be obtained by this process. So for example, his own equations, Paul-Level equations, like when Pillai formally proves that in the 6 families they are like this. Okay, sorry. Yes, so sorry. So actually, Nagel and Pillai gave a model theoretic criterion for a differential equation to be irreducible in the sense of Paul-Level. So it's a general criterion, but it implies that if it is strongly minimal and geometrically trivial, then in particular it's irreducible, so its solutions are never classical functions. So this is quite, for me, interesting connection between this very old classical notion of classical function and this model theoretic property coming from Zilber's trichotomy. So actually the full statement is that it's not irreducible if and only if it's analyzable in constants, for those who know what I mean, but it implies that.
So you mean,
so sorry?
There is an equation and you look at all the x's that you feel it. If this is minimal, then the equation itself is irreducible. That's what you mean?
Say again?
So you look at, not look at Pillai. You look at an equation and you look at all the x's fulfilling the equation.
Yes.
If that set turns out to be geometrically trivial, then the equation itself is irreducible.
The equation itself, oh yes, sorry, okay, yes, the equation itself is. Sometimes I call also equations like minimal and trivial, but yes, if set is like this, then the equation is irreducible. That is kind of interesting. Yes, exactly. Okay, so this is, and now we have also Zilber's trichotomy and criteria to check it. So you can in practice check whether some functions are classical or not. So actually Paul-Level claimed in 1895 that certain differential equations, for example, this nice one, satisfied by the J function. Yes, like this one. I think this was for him the original one, but ones of this form, some Schwarzian form. So he claimed they are irreducible. In particular, J function is not classical. But he never proved it. And then formally Theodose, Hassel, Freitag, and Naglu proved this claim by showing that many sets defined by this kind of operations are strong, minimal, and geometrically trivial in this article from Atlas. Actually, it was a little aside. The main point was applications like this Ax-Lindemann Weierstrass, but they proved geometric triviality of large class of equations of such form, including the ones from Palmer claim. And it was settled. Okay, so that's the end of the introductory part. So now we consider several. We go from ordinary to partial. So we consider several commuting derivations. This is, we have similar model theoretic language setup. And similar results hold. So Mark Gray in her thesis, PhD thesis, showed that this also has model companion. Now it's denoted CL0M. It's still omega stable, but it generalizes the previous one. The rank is now omega to the power n. It's not the rank, but larger. It still has quantified elimination. So now let us work in a monster model with two derivations. Okay, that's the point. So we still have Morley rank because it's omega stable. We can define algebraic dimension in a similar way. I just care whether it's finite or infinite, so there are more subtleties, but let's say it's defined in a similar way. And it was still claimed that dimension is finite if and only if Morley rank is finite. Oh, okay. But there was no argument. It was just she wrote something. It was written somewhere, but no argument is given. And then people started to think they couldn't find any argument. And then I'm not sure why it happened like this, but all the apostrophes should be this strange accent going to the right, and they were like this in the morning. I don't know why. Yeah, so it's over O, over A, and over E. So they started to work on counterexample to this claim. And then, okay, maybe they lost interest, I don't know, and they didn't. But then Omar was in Wrocław, he gave a talk about this in January, and Omar and I started to work about it. I'm not quite interested in that. So we picked it up. So what's the example? So exactly this one. So it's very strange in a way. So we look at the differential equation in one derivation, but we consider it in this model with two derivations. So obviously quite obviously, it has an infinite dimension now, because this partial 2 can have basically arbitrary values. You can get infinite Rassen's degree, as I say here. Okay, one could apply this one, but I was trying to convince you before that from the point of view of one derivation, it is non-accidental, because it was like the easiest one, the one with the simplest form, such that one obtains the trivial, which is interesting, strongly minimal set in the case of one derivation. Okay, so now we look at this simplest equation, but having two derivations in mind. And, okay. So can I call statements theorem if the proof is in progress? If this is the case now. now is proper accents. So as I was saying, but we have to be careful about this constant C. So we look at this set defined by this equation, but considered as in the theory TCF02. And what is very surprising, it remains strongly minimal. You cannot cut out anything interesting using the second derivation. Such a thing cannot happen if it was polynomial of degree 1 or 2. But somehow it happens now, which is not easy to show. So it's like strongest possible counterexample to this claim that with two derivation, dimension is finite, if and only if Morley rank is finite, because in this case, Morley rank is 1 and dimension is infinite. So, okay, so you have a fresh sketch of a proof. And what was also kind of new here, at least for me, that there was lots of help from good friend ChatGPT 5.5, which I will tell at the end of the talk. Huh?
Which version?
5.5?
I mean, subscription?
Yes, University of Wrocław is kind enough to give subscription. Okay, so what is the proof? What is the strategy? Actually, the human strategy of the proof. This was also the strategy of Zoe and Omar. There is a not very long model theoretic argument and Galois theoretic argument. Okay, maybe it's not that difficult. Showing that basically if A satisfies this equation and it's, let's say, non-algebraic or even not coming from the base model, then it's differentially transcendental with respect to second derivation, and this can be actually improved that for each R, if we apply R times the second derivation, it's not in the field generated by the previous one. So I'm not putting arch here. It's enough to show that. So so for each R there is such a statement, and in the ideal world there should be some inductive proof from R to R plus 1. So let's see what happens just for R equal 1. Okay, so for R equal 1, it says that partial 2 of A is not in the field M and expanded by A. In the other words, by contradiction, if it is in this field, so if you have rational functions such that this partial 2 of A is expressed by a rational function, then actually we can contradict that the assumption was, sorry to jump, but the assumption was all the time that the C is generic. The C doesn't satisfy any equation, differential equations at all. Okay, so to get contradiction, it's enough to show in this case that it actually satisfies. That then in such a way, this partial 2 of C is partial 1 algebraic. This will contradict genericity. So if you try to do this, okay, the biggest problem is, and this is, I think, when Omar stopped, if R is a polynomial, it's not so difficult, but if it's a really rational function, then you have to see what happens to the poles of this rational function, and things are getting more complicated. There are plenty of differential equations one should be able to solve, which is sometimes complicated. So, okay, so now how AI helped. So before, okay, so you have how to do inductive argument. Do it for 1, do it for 2, do it for 3, do it for 4, do it for 5, and maybe some pattern emerges. So we started like this. However, for 1 it was quite okay, even with poles. For 2, it became terribly complicated. And for 3, we were just stuck, so no pattern. And even doing this, there are lots of differential equations involved. So at some point I noticed I'm constantly making mistakes, so I started to ask chat, and it was not making mistakes, so it helped. But I was just asking, solve this equation, solve this, and it was some kind of pattern was appearing, but very locally. It didn't help with r equal 3, and sometimes the equation was so terrible that it was really depressing. And apparently it was not, this was working like on mathematical level, so not using the whole power. So then I got a bit depressed and lost my pride, and I just asked, okay, do it for r equal 1, do it for r equal 2, etc. And it answered, and for r equal 1, actually it was all the same, even slightly simplified argument we had. But for r equal 2, it was kind of shocking. It wasn't fully precise, but much better and much simpler argument than ours. And then there was kind of maybe something, maybe nonsense. But in this r equal 2 case, then the pattern was kind of visible. So, okay, so as I'm saying, then this pattern emerged for general inductive argument. I will not say this is still quite complicated, but without this it was getting hopelessly complicated, and somehow somehow I was focusing now. Somehow you have to work with rational functions in more and more variables, and to have argument, one has to fix the leading variable to focus on, and I was choosing the wrong one. I choose the good one. Okay, so last slide. As I've said, this is something very strange, which doesn't happen. So we have a strongly minimal set, we expand the structure, so lots of new things should happen to this set, but it doesn't. It remains strongly minimal. It is something strange. And still, if I started with sets, as I showed before, which were strongly minimal and not geometrically trivial, then actually it would not happen. The Borel rank will jump to omega. And something very similar happens when instead of second derivation, one adds automorphism. Actually, very, very similar statement is true by Wavy and Scanlon. So my main interest and motivation here is to find some general, I don't know even what should it be, but it would be very nice to have some general criterion, probably involving triviality. Like you expand the structure, but still you don't add anything to this definable set. You keep strong minimality. That would be very nice to find something general here. Maybe this particular equation is not that interesting, but such a general result would be really interesting. But I have no idea so far what should it say, but it should involve this triviality. Okay.
Thank you very much for your talk. Are there any questions or comments on the talk?
In your strongly minimal example that you just discussed, is the region trivial?
So that's what I mean by triviality. That's what.
Okay.
Yes. We believe so. But you remember, so actually it was Omar who proved Silver's trichotomy in DCF02 as he was talking. So I would have to check it against his. I believe so. But okay. We don't have proof for that, but I believe this. So even triviality would be good.
Other questions, comments? So I have a question about the GPT version. There are two paid versions, like Plus and Pro. One is 30 bucks monthly, the other one is like much more expensive, like 200. So which one are you using?
Knowing my university, probably the cheaper one. I'm not sure. It comes from Microsoft Copilot from the Office 365, and then it's 5.5. I'm guessing
All right, so thank you very much.
The next talk is in 10 minutes. Oh, there is a coffee break, so we have an hour.
Unless you cut. Jedno było widać.
Odłączyłem to, tylko że nie wiem, czy się wyłączyło, czy będę musiał znowu też włączyć streama i włączyć swoją tam. No, dobra.
Matki, mam do Ciebie bardzo ważną prośbę. Pokaż mi...
Nie, całkowicie już próbowałem i...
Według mnie to tam 11 nie było.
Mieliśmy podłączone zawsze, czyli tym kablem. Tylko, że
Nie,
mogę
sobie zrobić kawę najpierw?
Nie, no aha. Włączam kamerę, ale wciąż nie.
Tak samo jak ja ten plan. To sami robimy, nie?
To wtedy działało, że teraz na przykład ja chciałem włączyć tą kamerę, ale na przykład nie mogę tego zrobić.
Poczekaj, a co jak podłączę jeszcze raz?
No nic się nie stanie.
Loaded?
I should just check.
Okay.
Czasami tak
Okay, just take it out. Just check few slides. Okay, let me just download it.
Okay.
So I will just put for the time I will put the coffee break, but this.
Perfect. Okay. Can I leave my backpack here?
Yeah, of course.
Jestem kanoniczny i zaawansowator, właśnie przez coś takiego trzeba powiedzieć. Same w sobie.
Tak, dobrze, jak ten jest tak łączny, ma też rozwiązanie na kolejnym egzaminie, to jest na przykład.
Oczywiście to jest prawdą, tylko sprawdzane przez Ciebie jest właśnie, zastanawiam się, jak często to zdarza, w takiej sytuacji, jak to nie jest. To jest częste zjawisko.
Ja się chwalę, bo to jakaś...
Wtedy akurat klasa poszli. Nie
To jest chyba ale trzeba się nie można i nie... Też się płaci za to.
Jest plusem, tak.
Tego na klasę, ja rozumiem, że w wyjściowej przestrzeni chodzi o to, że każdy otoczenie się przecina. Przecina się gdzieś indziej, poza tym. A tutaj jak weźmiesz
Wtedy on to jest, i też program FEX, który matematycy testują.
Tak, jeszcze jest pytanie, jak określasz między nimi, czy jak bierzesz otoczenie, to zakładasz, jak bierzesz otoczenie jednego, zakładasz, że zawsze ten drugi siedzi.
Ale nie, ale też na przykład mam jakiś jest to prosty problem, a ja przecież odpowiadałem wywiadu, a to patrzy, nie jest zupełnie inaczej. Pominęłam, to ciekawe, jak one wywiadu, a ja jeszcze uwierzyłem sobie. Tak trzymałem zastrość.
I wtedy jak przetniesz te wszystkie...
No ale ważne tyle jest.
Ten też może być prosty, żeby masz kasy i dojść do...
Tak na przykład może być taka ala przestrzeni ludzkiego, w sensie właśnie, że tu jest dostawana budynek poszły otwarty, a na tym brzegu to są takie błyskoczone trójkąty, tylko kwestie osiepione. No wtedy na przykład jak się weźmie dwa takie punkty, to znalazł się przekonać. Ta klasa jest cała wtedy, tego jednego punktu z przodu, to ta klasa jest cały ten brzeg. Oczywiście wewnątrz to jest komputerski. Okej. I to takie przestrzenie. W takich przestrzeniach na przykład
w punkcie stałym. Ten punkt stały względem działania czego?
W ogóle funkcji ciągu. Funkcji ciągu. I tam rzeczy technologiczne są wdrażające. Znaczy tak, że przyjęliśmy zupełnie pokrycie, na przykład istnieje taka iteracja, do pewnego miejsca, iteracja punktów w jakimś momencie będą jakimś tam. Czyli istnieje taka rzecz, że tam odpowiednio to wszystkie iteracje już skończą.
I wtedy jak masz funkcję z x, a x, który ma tą własną.
Ciąg jest
Ciekawe, czy to jakoś w jakim uniformie można było też z tym założeniem, tak? Jednostajność w przestrzeni z jednostajnością.
Ale to jest to jest coś innego.
Nie. Ta rzecz to nie jest doktorat, tylko to jest coś dobrze znanego w dynamice doktorowickiej.
Ja tylko tam nie używam i dlatego
natomiast to jest jakby rzecz dualna, to znaczy nie, że te rzeczy są wyrazami, tylko iloraz przez to. To znaczy to jest dla grupy, bo dla przestrzeni to trzeba, nie wiem, patrzeć jakoś, że wokół każdego punktu to zrobić i nie wiem, jakąś relację równoważności, no zresztą nie wyrażam, nie przestrzeni. Jakąś relację równoważności z tym związaną, żeby iloraz przez to uchodzą. Ale dla grup to wiadomo, to jest przekrój tych wszystkich właśnie, on jest tych grupą normalną i jak wydzielimy wszystkich z tego to jest ten największy iloraz Hausdorffa. To jest metoda, jak zrobić z takiej grupy nie Hausdorffa, tylko Hausdorffa. Bo jak jest grupa topologiczna wtedy, to znaczy, że działanie jest jointly continuous, ale ona nie jest Hausdorffa, to wtedy po prostu wydziela się przez dotknięcie elementu neutralnego. Wtedy się dostaje grupa jak Hausdorffa psychologiczna. Ale tu, jak jest tylko działanie separate i continuous, to nie działa i to się przez coś takiego. To jest jakiś związek z takim ogólnym ciekawe, to wygląda. Jakoś sobie pomyśleć z tego. To macie pracę, tak?
Tak.
To jest coś niedawnego?
Tak, niedawno.
Mam do Ciebie taką sprawę, pytanie, czy tutaj może mógłbyś coś poradzić?
No.
Myśmy z ostatnim wyszedłem na PTS i też w sprawie jakości i tak dalej, jakby tutaj zrobić coś takiego, żeby te przedmioty tak około bardziej spójne, żeby to się nawiązywały. Wiesz, że stworzę taki pakiet, a nie po prostu nie zależy od
przedmiotów gdzie?
Jest na wykładzie na matematyce, nie? Po prostu
ale w sensie to Warszawie?
Tak.
A, okej.
Na przykład właśnie no, że wiesz, właśnie jakie tematy na jednym przedmiocie w wykładzie mogą się pojawić w czymś innym i Piotrek Szewczak będzie prowadził profesorsingu w szkołę. No i tak się zastanawiałem nad tym, czy dałoby się możemy podrzucić jakieś takie, wiesz, na poziomie zadań można ćwiczenia, ale coś, co jest związane z interesem, czy pewnością, coś, co można by przepracować. I wiesz, że wtedy wymagało wstępu, żeby trzeba było opowiadać przystępy z półtorej godziny.
No tak,
tylko że to można było zrobić. Ale można sobie wyobrazić, że nie w przyszłym roku, tylko że w kolejnym roku będzie miał wykład między innymi historii polskiego. Także można sobie traktować, że studenci już będą obiekty znali podstawowe definicje pojęcia. I wtedy nawet mogło wymagać tego, no ale wciąż na ćwiczenia, albo na przykład na pół godziny wykładu, a nie na takiej zasadzie, że robię sobie jakieś dużo rzeczy. No tak sobie pomyślałem, że może powie coś, że może to miało być jakieś tutaj pomysły, że coś porzucić tego rodzaju.
Jakieś takie zadanka, to sobie przeciw jakieś takie procedurowe aspekty związane z materiałem.
Tak. Wiesz, jakieś coś przygotowy, wiesz, to wystarczyłoby niemożliwe, ale chodziłoby o to, żeby na przykład właśnie, żeby właśnie też pojawiły się tak, czy coś związane z tym. Na teorii modeli się pojawiły też się pojawiły.
Udowodnić, że jakaś tam taka prosta reprezentacja po prostu jakąś egzotyczną mieli, która nie jest izomorficzna. To żaden izomorfizm z normalnymi liczbami nie jest model wyjściowy. To jest taki rak rozprostości.
Na przykład, a jakby to było jeszcze coś, wiesz, coś takiego, co było, miałoby, żeby tam było na przykład rano, że to wiesz, nie było publiczno, wiemy, to tam nie uznać tego za... Znaczy, to jest to, jasne, ale...
Ja to jest takie, że
może to nie nazywać się teraz, no, coś naprawdę, wiesz,
no tak.
No tak podrzucam, nie? Jak ci coś przyszło do głowy, jakby, wiesz, jakby podrzucił no właśnie, idea jest taka, żeby już wybudować jakieś powiązanie i
to co by to na pewno pomogło, to gdyby na przykładzie stolinności. I to inności, to coś, nie wiem, to dalej tak zakres.
No, tak, ale wiesz, ale to czasy też mamy trzeci na wiele czasu. W związku z tym to się już zmieni. A że co wprowadzić?
No to się podbudamy. To jest takie coś, co dzieje to innego się stanie.
Wiesz, ale z drugiej strony na przykład na wykładzie walki będzie na przykład.
No że tak, na wykładzie to się pojawia.
Co i wtedy jakby
że w logice to one się pojawią w takim abstrakcyjnym sensie w ogóle, jak to będzie podsumowanie elementarne. W to mnogości to one mogą się pojawić jako stricte podwody elementarne jakiegoś VK-a. Jakieś takie proste zastosowania, jakichś argumentacji. Takie podwody elementarne w to mnogości się stosuje.
Ale żeby to można było wykorzystać właśnie, czy mówisz ogólnie,
żeby ogólnie, że jak człowiek skończy ten wykład stolinności i pójdzie na forcing, to żeby już miał to pojęcie modelu elementarnego VK jakoś zinternalizowany i model Foxing zrozumiał.
Okej, w tym sensie, no tak.
Czy Perfect Foxing, czy jakieś różne argumenty, w których mogę już w ten sposób.
No tak, to też jest kolejne rozwiązanie. No tak, dokładnie. No, jakby ci coś przyszło do głowy, to byśmy to na znacznie
no.
So there is this one that you can attach to your shirt. So yeah, so which one you prefer? Oh no, I don't attach to your shirt. Oh, maybe the other.
Yes.
Okay. So here's the pointer.
And you erase the button, which is American.
No.
Okay, so the pointer.
Okay. Everything is right. Do you have the pointer or?
Yeah, the pointer.
So it's this one's going further, going back, and the pointer later is. Mamy tylko zapasowe do tego, że nie są Yes, everything's going okay. Like, tomorrow we'll get to change the batteries, but it's working out.
Okay.
Right, so
Our next speaker is Alessandro Andretta from the University of Turin, and he's going to talk about Sierpinski's theorem and its influence on geometry of space.
Okay. Well, first of all, I would like to thank the organizer for inviting me. It's a pleasure, it's an honor to talk here, and I'm really glad that I will talk about some very recent results that are connected with the results of one of the great Polish magicians, and Sierpinski. Okay, so there is a saying, apparently due to Paul Almas, that a topic can never be too simple or too short. I might try to disprove this thing. It's going to be really quite simple. Probably, I try not to put too many details. So maybe I'll disprove a conjecture of Almas. That's a big thing. Okay, so the general theme is the question is, how can we cover the space with finally many small sets? By space, I mean, by space, I mean R to the D for some D greater than 2. The smallest means having finite or a countable intersection with geometric objects of a prescribed kind. The archetypal theorem in this respect, the archetypal theorems are these results to Sierpinski in 1919 and 1951. So the first one from 1919 says that the continuum hypothesis, CH, is equivalent to the first one, this one here, and R2 the plane can be written as the union of two sets, A and B, such that every horizontal line has countable, so it's kind of countable, considered to be small, has countable intersection with A, and every vertical line has countable intersection with B. And so this is a nice characterization of the continuum hypothesis in geometric terms, so to speak. But apparently Sierpinski was not completely happy with this result because the notion of countability is not absolute. But in 1951, he managed to prove a better result in this respect. R3 can be written as the disjoint union of three sets, while in terms of disjoint, you can get disjoint. It can be covered with three sets A, B, and C, such that every line parallel to the x-axis is finding intersection with A, every line parallel to the y-axis is finding intersection with the second set, and every line parallel to the third axis is finding intersection with the third set. Now, so this is in a way a much better result because being finite is really something concrete. And obviously, these sets cannot be measurable, nor they can have the property of pair, because, well, look at the first one. If A is measurable, if A were measurable, then you look at all the vertical section, you say vertical, horizontal, every horizontal section of A, these are supposed to be countable, so if it's measurable, you apply for B, and A would have to be measure 0, B would have to be measure 0, and then so it's a contradiction because R2 is not of measure 0, and similarly for the second example. So some notation by E1 and EK, I mean the standard basis for R to the K. The line in R to the K is parallel to E sub I is a set of that form. So you give me some parameters and you make the ith coordinate there. Now, this notation of course makes sense even if we replace R with any set. So get talk about an affine line with x to the k, obviously. And the previous theorem was generalized by Kuratowski I mean, the previous theorem of Sierpinski and the paper by Kwiatkowski appeared in the same issue of fundamenta. And it's always difficult to understand who wrote what before. But this theorem is in some sense it encompasses the previous one. Okay, take any set X, and suppose delta is an ordinal, say delta is equal to 0. Take delta is equal to 0. Then the size of X is at most aleph delta percent aleph n, delta is equal to 0, is the same thing as that we can decompose, we can write X to the n plus 2 in n plus 2 many sets, such that every line parallel to E sub I intersects A sub I in less than aleph zeros. It's going to cardinality less than aleph 0, maybe 5. So when delta is equal to 0, then n is equal to 1, we get the previous theorem. What does it say also? That if we take R4 and we decompose it in 4 sets, so that every line has finite intersection, that the continuum is at most aleph 2. Or if you take R3 and you allow countable intersections, you get aleph 2. So, this is, if you want countable intersection, you put delta is equal to 1. You get essentially everything here. So this is a characterization of the alephs of being of size less than aleph something in terms of this geometric property. Okay. In the following years, actually decades, there were several generalizations of the theorem before, of the theorem that we have mentioned before. So let's look at Sierpinski's theorem for R3. Okay, it's really good because it has finite intersections, but we have to give up something. We have to move from R2 to R3. So the question that Erdős posed, is it possible to have a geometric statement that's equivalent to CH and use some sort of finiteness, and it just talks about the plane and not the three-dimensional space? So, synthesizing, putting together, we still various papers from Bagami, Davis, and also something like Erdős from the 60s to the 70s, we can get the following result. The continuum is at most aleph delta plus n, even only, let me say it one way, there are pairwise non-parallel vectors u1, un plus 2 in R2, and there are a1 and plus 2 sets over R2, such that every line that's parallel to ui has finite or countable or whatever intersection with elements. So now if we wanted to find an equivalent statement to CH, what would we do? So we take the plane and we choose like 3 vectors. Well, I can choose this one, and this one here. So CH is the same as saying that you can count the plane with 3 sets, such that every horizontal line intersects the first in a finite set, this one intersects the second set in a finite set, and the same from this direction. If you want to have the continuum at most aleph 2, you get another direction. Should be different from this one, but don't take this vector here. It doesn't work. Now, so I wrote there are or for any. Yeah, because you can choose the vectors as long as they are pairwise or parallel, or if somebody hands you, give you a decomposition with some specific vectors, well, it's still equivalent to that assumption. Okay? Now, so yeah, this is a way of some sense compressing this terminal bound, writing encoded in the way. And I'll come back to this result. So in particular, you can also state it like this: the continuum is at most N, if and only if there are angles θ1, θn plus 1, and there are sets up to n plus 1 covering R2 such that each line with slope theta I has countable intersection with AI, or if you have one more angle, you can go down to kind of finite intersection. Okay. So you can also do some sort of like dual definition. By this, I denote the set of all affine lines in R. So we have this resolved by Erdos and Davis from the early 60s. It substantially generalizes what we've done just so far. If you give me, so in the picture here, you have like 1, 2, 3, 4 kind of lines. The one that are horizontal ones, the vertical ones, the one according to the first law and to the second law. If you just choose randomly, so to speak, collections of lines, alpha 1, alpha n plus 2, in the family of lines, they have to be pairwise disjoint. Then, assuming this hypothesis here, you can find A1, AN plus 2 that cover R to the D, such that if you take a line in the ith collection, L intersect A sub I is less than R of delta. Okay, so it's kind of more general. Okay. Now let's see some further result relating. Actually, I should mention this. Look, the theorem of Kuratowski was talking about the size of the set X, general set X. Here we cannot replace the real line with X because we have to talk about vectors or slopes or something like that. It's really important that you use R of this group or something like that. So geometry here comes in a little bit. It's a little bit more substantial than the original theorems. And in 2001, Comiat introduced the following concept. He just talked about Aleph zero cloud. What's an Aleph delta cloud? With center C is a subset of the plane, such that this is C, this is a point, such that if you take any line departing from C, any ray, then that line will actually intersect the set capital C in Aleph delta, less than Aleph delta points. So you're sitting in C, and whichever direction you look, you just see finally any points of set C for cloud. A cloud is just an Aleph zero cloud. Now, the continuum, the Comiat proved this result for delta is equal to 0, and the same proof is actually not this result actually can be extended. Comiat proved it for delta is equal to 0 with some minor tweaks. You can prove it for general delta. The continuum is less or equal than Aleph delta plus 1. Well, this one implies that R2 is the union of n plus 2 many Aleph delta clouds with non-collinear centers. And CH hold just in case the plane can be covered with 3 clouds with non-collinear centers. Well, why do you want non-collinear centers? Because if you have 3 collinear centers, you look in the direction of the collinear center, the first cloud will just, a ray from the first center will just see finitely many points there. the same is true of the other center. And you just touch finally the points where you have continuum points. It turns out that this is the only obstruction because you can change the proof a little bit and prove that if you give me 3 collinear points, I can find 3 clouds that cover everything except that line. So it's really just a minor obstruction. So I mean,
but some of these points may be collinear, yes? You are assuming that it's not the case that all of them are collinear, but for example, some 3 of them may be.
No, okay. If you want to have this thing, you have to have 3 clouds with non-collinear points.
Yeah, but in the first.
In the first one, okay. For the implication, you can do it also with non-collinear, but you can get actually an if only if, and in that case, you have to have that. Okay, in this case, non-collinear means not all collinear. Not all. Yes, this is a good point. Not all, not collinear. So this one is. Okay, now you see this is really much more geometric than the previous one, than the previous results. And Schmer, starting from that, actually proved what Comet wasn't able to prove. Comet proved that 2 to the 0 less real than alpha n implies that the plane can be covered with n plus 2 multiplied. There is always a number of continuum alpha 1, you get 3 clouds, 1 plus 2, basically. So if you want to cover with from less real than alpha to the n, you have n plus 2 clouds. But Schmer actually got this equivalence to prove the other direction, essentially. The plane can be covered with n plus 2 many other delta clouds whose centers are not all collinear. So in these preceding theorems, the sets used to decompose R to the D. Okay, here I was just talking about R squared, but you can do the same thing also. You can talk about clouds in R to the D, D3, and analogous results. The sets are neither the measurable nor they have the property of data. So they cannot be sigma 1 or pi 1 or the algebra things. But can they be sigma 1 too? Tortis and Weiss, I forgot to write, but they proved it. It's 2018 or something like that. Reasonably recent. 2014. Okay. Proved the following really is maybe really beautiful result. So what's stronger than CH? Well, every real is constructible. Every real is constructible is equivalent to there is a Sierpinski decomposition of the plane where the pieces are sigma 1 to light phase. Okay? Or there is a Sierpinski decomposition of R3, light sigma 1 pieces. Or R2 can be covered with 3 clouds. That's that down here. Yeah, so I mean, this one is a variant because in here we are using just kind of like here we are using R3. Here we are doing what we were doing here, like U1, U2, and U3. Imagine it's just one. Okay, so and in fact the proof work does relativize. Big saying real and subset of omega, then say that R is containing L of A is equivalent to characteristic decompositions with pieces which are similar to in A. Okay? So, okay, now there are two possible directions where one could investigate. How about if we ask for higher complexity, like sigma 1 or 4? Then, you know, my knowledge of finite model theory falls flat, and there should be sort of like an analogous result for some appropriate inner model that should play the same role as L. We looked at that with Lorenzo Nadaro, who was a student of mine, and Raphael Canois. And we thought, well, how about if we look at these other theorems of Sierpinski, they're saying that the continuities are lost out of 2, out of 3, out of 4, even only if there are decompositions of certain kinds. How about if we ask those decompositions to be sigma 1 something? And so before we go into the formal statement, let me just remind you briefly of the constructibility decrees. For A, B subset of omega, say that A is constructible for B if L of A is containing L of B. Two things are reconstructible if one is less than the other, according to this constructibility degrees, then they give the same at all. And this is the constructible degree of the set A. So it's like 2 ray degrees, but with a portion notion of equivalence. Okay? Now, there's a bit different though. So DC is called the upper semi-lattice of constructibility degrees, and for A and B in this collection, well, of course, A is less or equal than B, if only for any representative this relation. Okay? Now, this structure is highly non-absolute. In fact, if B is equal to L, it's a singleton because every real is constructible and just add 1 in generic class. So if we just add a single such generic real, then D sub C is a chain of like 2. So the constructible reals, and then those guys which are epiconstructible with this Sachs real. Sachs reals are minimal. There's nothing in between. If you add a quite generic real, then in that universe, actually at that point, then D subs this C is for the coin-generic real, has nothing to do with the substrate here. The font is actually slightly different. So, but D sub C means the constructible degrees. So if it bothers you, forget about the C here. And the C here is for coin-generic. Then, D sub C has lots of chains and anti-chains. In the iterative Sachs model, the continuum is out of 2, and D sub C is a chain of length out of 2. And in fact, by a result of Zofia Galovic from 1977, if you take any well-founded upper semi-lattice with lowest element, and this P is inside L, and L thinks P is countable, so it has to be constructible and constructively countable. Then there is a generic extension of L in which D sub C, the constructible degrees, are isomorphic to P. So it's kind of like it's a really complicated proof. We try to really hoping to get some inspiration for further work, but it's we have to give up. Anyway, so sorry. So suppose you have, this is a theory organ theoretic notion. Suppose you have an upper semi-lattice. a finite set F is said to be redundant well, the finite set, you take a P from F, you take it away, then the element P cannot be below the sum of the other elements. Okay? So you have 15 elements, you take one of the off, you take the sum of the other 14. The sum of the other 14 is not about the one that you take away. It's a sort of algebraic independence, so to speak. Now, so if you have this equation, you say that F is, if you can take away one of the elements is redundant. If that's not the case, F is irredundant. Every time you take it off something, you lose something, so to speak. And the breadth of P is the supremum of the combinations of irredundant subsets of P. We're going to see some examples of the if P is an element, we say that P has breadth at most kappa about P. If you look at the sub-semi-land is above this one, so breadth at most kappa. So some example. Suppose P has got breadth n. If n is equal to 0, that means that P is a singleton. That's by definition. If n is equal to 1, well, this happens exactly when P is linearly ordered with these two elements. If you take one away, you have two things. If you remove the one element, you get something without. And if n is at most 2, is at least 2, then P has anti-chain of size at least 2. So there is a theorem by Eator that's actually quite interesting from a theoretical point of view, which says that if P has got breadth n bigger than 0, and every predecessor of the point is finite, then the size of P is at most alpha n. It's kind of interesting. So that now let's take this thing together with the previous results. With alpha sub I, with this notation, I mean all the lines that are parallel to E sub I. So with Lorenzo Artaro, we got this equivalence, then you can get a Sierpinski decomposition in Rn plus 2 with n plus 2 many sets, with sigma 1 to A sets, with sigma 1 to sets. If and only if these C, the constructible degrees, has breadth at most n. So rather than saying that having some bound on the continuum, we have some algebraic notion of narrowness of the constructible degrees. So how about if we take n equals to 0? If n is equal to 0, then dc has breadth 0. dc is a singleton that says R is contained in L. And if n is equal to 0, you get exactly what Torquist and Weiss proved in the previous case. Okay? Here we have countable intersection, here we have finite intersection. But, well, this is sometimes is the correct generalization of the results for his bigger decompositions. And of course, we can relativize, but now we have to say that the constructible degrees has breadth at most and above some place, because what happens before it's irrelevant, but above there, the breadth, the width is not too large. Now, this is really embarrassing. What about clouds? We don't know. Torquist and Weiss were able to prove it also from clouds, but we are not allowed. Maybe because they are better than we are, but actually there is a motivation here. Okay, so in order to do this kind of computation with breadth, we really need to have this kind of like rectangular construction that's given by the decomposition of R to some power. Instead, when you start looking at clouds, you're playing the doing things in the plane, and we are not able to prove that from the first assumption, E as breadth plus n. Then we can show that R2 can be covered by n plus 2 times. This is what it's like.
But you can go the other way.
Yes, for some other reasons. Because using consideration from elementary geometry, one can show that if R2 can be covered with n plus 3 clouds, with some clouds whose centers are not ortholinear, then you can get a statistic decomposition, and therefore by the previous result you can get this. So the idea that I'm trying to convey is the following. When you do this kind of construction on the plane, you're actually proving something more complicated than proving something for R3. I mean, from the fact that the plane can be divided into 3 sets such that every horizontal line intersects the first one in a finite set, every vertical intersects the second in a finite set, and every diagonal line intersects the third one in a finite set. That statement implies in ZF, there's a geometric construction to construct a serpentine decomposition of R3. You do it by hand. And once you're in R3, you can, we were able to perform that construction. So there is something fishy going on here. Not fishy. I don't know. It seems that we don't understand well enough this problem. And now I want you to get to how much time do we have? Well, I think so. What's a spray? A spray is zero spray, so think about that as equal to 0. Is a set with a specified point. Oh yeah, I forgot to mention. The center of a spray or a cloud need not to belong to the cloud or the spray. It's just some chosen point. And here, rather than looking in this various direction, we draw a lot of circles centered in this center. You're here, you draw a bunch of circles, and each of those circles has to intersect the spray as infinitely many points.
The definition has line.
Yeah, yes. Cut and paste is twice again. Sorry, thanks. I mean, I looked at this a few times. You never, but the picture is that correct. And it took me a long time to do the picture. Yeah, so sorry, here, I mean, such that every circle centered in C has finite intersection with S. Okay, so look at the picture, don't look at the definition. So the theorem by Schnell says that the continuum is a non-style effect if and only R2 can be covered with n plus 2 sprays with collinear centers. So CH if and only if R2 can be covered with 3 sprays with collinear centers. Oh, needless to say, also these guys are that I measure all blah, blah, blah. And if you ask me, can you add this thing to the previous list or the same one to list and say, I don't know, I cannot do it right now. Okay, so the reason why you want nonlinear is because De La Vega and Schmel proved that R2 can be not, that's a ZFC result with 3 sprites with non-collinear sectors. So De La Vega proved it for equilateral triangle using some computer, I don't know if they use mathematical or something like that to solve the sprite equations, and then Schmel actually proved for any triangle. So yeah, if you give me a bunch of points and you get 3 of them which are not collinear, then you can run the argument in parallel way with just three sprites, and then you add a bunch of foreign sprites with against. Okay, so they have to be all collinear, to be meaningful from our point of view. So R2 cannot be covered with 2 sprites, it's too hard. But CH is equivalent to R2 being covered with 2 RF1 sprites, actually. So sprites such that each circle touches countermeaning points of the spray. What about sprays in higher dimensions? So an RF delta spray in R to the D is a set with the points such every d-dimensional sphere center C intersect the given set S in less than RF delta points, so you take spheres. So they are sparser and sparser as that. R3 is not the union of n many sprays with collinear centers for any n. And the analog for R3 of being collinear in the plane. In the plane, we wanted to have collinearity. In the space, you cannot have collinearity. But what's the analog? Should be what the right analog is belonging to the same plane. So let's say in R3 that belong to the plane here on the floor, and no 3 points should be collinear. So it's some sort of like being in general position. Actually, it is being in general position. So this is the result that I got when I was visiting Vienna with a geometer. So the following are equivalent. The continuum is at most RFN. R3 is the union of 2n plus 3 sprites with centers belonging to a plane, in such that no 3 of them are collinear. Or R3 is the union of 2n plus 1, 3 equals 1. And here we have sprays which are RF1 sprays, namely the intersection is at most countable. And the condition of the centers is the same. So CH is only R3 is the union of 5 sprays with centers, blah blah blah. And R3 is the union of 6 sprays also. It's just, having 5 or having 6 is the same. But then if you have the continuous of most RF2 is like saying that R3 is the union of 7 or 8 sprays. So it goes on 2 by 2. And R3 is not the union of 4 sprays where the kind of centers are lying on the same floor. In fact, actually, there is a. So let me give this definition. A set of vectors here in R3D is in general position if any D, any of those, for the basis. A set of points P of an affine space of dimension D is in general position if just a affine span of K plus 1 many points of P has dimension K. So they're kind of like yeah, they are in general position, so to speak. And, oops, sorry. Twice. So for any dimension d, you have a bounded continuum, if and only if actually d is the union of this main expressed with center belonging to some hyperplane H, and the centers are in general position in this ambient space, in H. They're kind of in general position as much as possible. Or if you want to use Aleph sprays, countable intersections, you are allowed to go from n+1 to n. Obviously, if there is an analogous theorem for Aleph delta sprays, but there is no point of avoiding this thing full generality because it just creates some noise, so to speak. Now, so this is a table. The one on the left is for sprays, regular sprays, finite intersection. The one on the right is countable. And above you see the number of sprays, these the dimensions, the vertical bound, and this is sort of like a table that summarizes the situation. So when d is equal to 2, you get the Schmerl-Lenadecker results. The Schmerl result. And well, this is the so irrespective of the size of the continuum, R3 cannot be covered with less or equal than Aleph for sprays, as long as the center are coplanar. What if the centers of the sprays are not coplanar? How about if I give you a tetrahedron, at the vertex of the tetrahedron, 3 points on the floor and a 4th point here? Okay. My attitude about whether or not this is possible follows some sort of sinusoid. Certain days I think it's possible, certain days I think it should not be possible, and given that the guts to say that most likely it's not true in the paper. But, okay, let me frame this thing in a slightly more general setup. So there is a beautiful theorem by Elders, Jackson, Mauldin, which in some sense subsumes many of the results, actually just about every result that we've seen so far about Sierpinski, Davis, Magenil, the composition. And this thing implies that if you give me 5 points in R3, I mean, the result is much more general than this, but I'm applying to R3. If you give me 5 points in R3, such that no 3 of them are collinear, then if you assume CH, R3 can be covered with 5 sprays centered in those points. So 4 points are not enough to apply this result, but if you give me 4 points on a plane and a point here, good. 5 points on a plane and they're in general position, good. And that's what we use anyway. But I don't know if this assumption is necessary for the general case. If they are on the plane at 5 points and they're in general position, then by our result, yes, that implies CH. But what if they float in space? Okay, so some open problems. So can R3 be covered with 4 sprays with non-coplanar centers, i.e. the vertices of a tetrahedron? Second question, suppose R3 can be covered with 5 sprays whose centers are the vertices of a pyramid and the quadrilateral base. Does that imply CH? It follows from CH, but is that equivalent to CH? Suppose you have 5 sprays whose centers are in general position. So, sorry, it's not the case that 4 of them are replying and the other one's speaking up, because otherwise it would be the case too. Does this imply CH? Now, a little confession. I'm really grateful that Yaroslav didn't pester me to send an item and abstract too early, because had he done it like a few weeks ago, I should have stated in the statement. And I can prove that then the answer to question 1 is no. I still have some hopes with that. In a paper with Ivan Itzvested, we even said that we thought that this was provable in ZFC. I don't think so. But, so this is what I suspect, and since there is no more time, I just.
Thank you very much. Are there any questions or comments?
So in your theorem with sigma 1, 2, with the degree partial order, do you use Titor's theorem in your argument or not?
Not quite, but so at some point, so I wanted to state that because it's a really nice theorem because it connects kind of like the size of the continuum. At some point, I had some hope to show that if the constructible degrees had some limited width, that would imply some bound. But that, I couldn't get anything better than what CRPC theorem does. I mean, sort of mentioning the first theorem was not strictly necessary for the logical dependence theorem, but it's a beautiful theorem which I was not aware of, and we discovered it in the literature. Actually, Frederick Baron told us, well, there's this beautiful theorem that sort of says something, but it's not good enough to give some kind of more stringent result.
More questions?
And concerning the sigma 1 tone, are there some reasons why phi 1 2 is impossible, or maybe we could go to delta?
You have a partition. So once you have a partition, you can take partition in sigma 1 2 sets. So these things are also delta 1 2 sets, and you see that the problem is that these species cannot have the property of there, so nor can they be the backmeasurable. And all the tricks that are found about getting some insight in the structure of the constructible degrees is that, well, let's add a point generic real. Let's add a random real. But if you add a point generic real over L, then you get there is this result by Yuta Shella that is that every sigma 1 set has a property of A. And so you cannot do that because otherwise you don't have this CRPC decomposition. So you have to link with the existence of these pathological sets, and you would like to say something. And so we retreated to this notion of breadth of constructibility degrees that we got solved.
All right. So let's thank the speaker again. The next talk starts in 10 minutes and it's going to be online.
Będziecie zrobić własne. Jest
Okay. Hello, can you hear us? Okay. Okay, one moment. We will try so we see you.
Nie ma możliwości, żebyśmy zobaczyli, żeby on nas zobaczył.
Nie ma, czekaj.
Ale nie ma.
Spróbuj to spalić.
Jeszcze sekundę. Trzeba zainstalować OBS Studio.
Dobra, nie inaczej, to daj mi, tam leży mój komputer. Albo... O. Bartosz? Dobra, to tak. Ty masz pełną baterię?
No, to mam
To zrobimy tak.
na moje ręce, czy... Aha, no, nie masz ładowarki, bo ja mam, bo mogę podłączyć. A nie, kurde, zostawiłem swój...
Okay. Hello.
Musisz zmienić głośnik też tutaj, żebyś słyszał.
Myślę, że słychać.
Tutaj to słychać, tylko że ty nie słyszysz, jeśli coś mówię teraz.
Dobra.
Jak chcesz, może obrócić tego laptopa. Ja nie mam. Masz jakąś ładowarkę?
Nie mam.
A jaką potrzebujesz? C?
Tak.
No to poproszę go, może ktoś ma.
Yes, we see the screen well, and I'm pretty sure. Okay, just a second. No, I'm pretty sure you are. The audience hears you. I am on the other side of the speaker. Yeah.
To nawet dobrze. No bo wtedy tak, jak to jest w rozsądnych granicach słowotwórstwa, ja to położę tego laptopa, bo już nie mam siły dotrzymać. Jak to jest w rozsądnych granicach słowotwórstwa, to fajnie, bo to wtedy temu nadaje sens. A random mi się bardziej podoba niż to draw.
Okay, so
do random draftu, nie?
We see you well, and we will try. Just a moment, okay. Bartosz, idź tam. May you try to start speaking? Okay, so you are well. People hear you well. So it will work. This is. Okay. So I will leave this camera on so you can see the audience, right? So I will put it that way. Okay. Yeah, okay, so we still have like how much time?
Coś mówi do ciebie, tylko
Okay. Sorry. The problem is I'm right next to the speaker's table, and I hear you very bad because the speakers goes the other way. And if I go there to listen to you, I will lose the ability to speak. Yeah.
Jestem potrzebny, czy mogę sobie czekoladę zrobić?
Możesz. Okay, so we will begin in 5 minutes, right? And I think it's all will be good.
Zrobili z tego postęp, że no z inkluzją po prostu. I potem do Czech właśnie chyba z tym posetem potem forsowali i udowodnili, że ten poset to jest tam daje takie same wyniki jak jakiś saks zbudowane, splecione z czymś tam i tak dalej. No i teraz my robimy grafy podobne do grafu Rado, ale nie graf Rado sam sobie, które też mają takie mocne samopodobieństwo. To znaczy, graf Rado ma tą właściwość, że jak weźmiesz punkt jeden pojedynczy konkretny, to spojrzysz na jego wszystkich sąsiadów, to jest jeden zbiór, i spojrzysz na jego wszystkich niesąsiadów, to jest drugi zbiór, to oba te zbiory są izomorficzne z grafem Rado. A teraz było takie pytanie, czy to jest charakteryzacja grafu Rado? Nie jest, no właśnie, nie jest. No i teraz my właśnie badamy te grafy, które mają tą własność, a nie są grafami Rado. No i one też mają takie mocne samopodobieństwo, więc ten poset też mógł być mocno taki nietrywialny. I ja bym te posety chciała pobadać, bo może być ciekawe właśnie z punktu widzenia forsowania tego. Tylko, że ten... To tam kilka prac z tego poszło. Tam było już 3 chyba autorów. Chyba tak.
Dobrze, tutaj usiadł, żeby zapowiadać. On słyszy z tego.
Dobra. To może już tam zaklaskać, nie? Żeby już ludzie przychodzili.
Tutaj widać nas.
All right, so the last talk in the afternoon session will be given by Itai Ben-Yakov from the University of Claude Bernard Lyon. And he's going to talk about, okay, so the title of his talk is Towards First Order Quantum Logic. A few thoughts on continuous logic, affine logic, and what's between them.
Okay, thank you. Thank you for the invitation. Apologize, what would be I'm not spoken out about
Gdzie ty?
Okay, what kind of question do you know? So you know nothing about this question. Yes, no. Or maybe later we ask quantitative questions. So we want the quantity, the real quantity. What is thought, the height of something, the length of something, the distance of something, whatever. And then maybe later, so some physicists might ask, okay, what is the position of that electron? And okay, and then they ask you what is the momentum there. And of course, it's a tricky question because if you know, if you measure the position, you lose information about momentum, and vice versa. And okay, I mean, definitely don't pretend to be anything even close to knowledgeable in quantum mechanics. But basically, this is accounted for in one formalism by saying that position and momentum are observables that are coded by operators, and these operators. Okay, but this is absolutely out. What I'm going to do. Let's start with the thing that everybody knows. There's no questions, so atomic questions are just two questions. It's true, it's false. You can space these questions and maybe combine them using Boolean connectives. So that basically propositional logic. And all you know, yes, it can apply semantic. First order primitive logic is every positive number squared using quantifiers and okay, so this is the kind of thing that I don't expect actually to tell you anything new here, just to say that. Okay, so next kind of question is quantity. I want to be. So I can ask what is norm of something, how far is something from something, stuff like that. So I mean, if you really insist on just using binary logic, then you can say, okay, you don't know the norm of x, all I need to know is whether it's greater or equal to q for each rational q, and then okay? That's true, but that's not quite right, because that means that, okay, we have infinite many answers, they have to be consistent, they have to be better than consistent with more to avoid infinitesimal, or not to be infinitesimal. It's not the best approach, at least as far as I'm concerned. So, really, let's just accept that we want a real value as an answer to a question. So we want a real value. Okay, so now let's just pick something. It's a technical hypothesis. It doesn't really, it's less constraining than it seems at first, but just say that in the same way that the set of binary possible answers, true and false, it's a compact set, I'm always going to consider real value questions which the possible answers form compact. It's technical, don't worry about it. Just say. Okay, and then this is a thing, this is to be interesting. So I start with signature, so the different system predicates, predicate symbol, sorry, so each symbol has a guarantee as usual, and okay. I said I want these to be compact, but I also want bound for each predicate, and then I'm going to define structures. Again, more or less as usual, the interpretation of a predicate symbol is the function from the right arity to the base, but I want to set it up. Okay. And then I construct formulas, I have atomic formulas, and I construct more complex formulas using continuous connectives. So, okay, so I have some choice about what connectives I use. You can use
dry connected, you can use lattice connected. In fact, you can use all of these. It doesn't really matter because at the later stage, you are going to complete analysis of the race and then solve by facing terminals. Any of this system of simple connecting just you get. Okay, so you get continuous connectors, continuous. And quantifiers, there are suit and pins. Okay, you deal with these things naturally. And okay, it's the thing that bothers sometimes people sometimes is that I consider zero as being true. Sometimes just being less or equal to zero should be considered as true. It really depends how you formalize things. Okay, just I mean, easiest thing is just to give an example. So, for example, say that you have a unit ball. So I want bounded things. So I have a unit ball of space, and I want to know if it's actually a Hilbert space. So I will test the following identities. Okay, so I take one side minus the other side. I want that to be only 0. So okay, then let's square it. So now I want it to be 0 if it's non-zero, it's positive. So let's take the supreme over all possible instances of this potentially positive number, and I don't want to be positive, I want the supreme to be 0. So this is an example of a sentence actually that knows variable. So this sentence vanishes, is true, even only if my Banach space and actually these similar sentences I think axiomatize the class of uniforms or Banach spaces. So okay, in a language that only formulas are going to be norms linear combinations, addition, multiplication are connected, and then so forth. Okay, so you can do this in many situations. It actually turns out to be quite successful, useful when people use it for real value and make it such. Oh, sorry. Just one thing. I'm completely going to skip the metric. So usually we say that we replace equality with a metric. It's complete and blah blah blah. Okay. Today this is not going to be very much, so I'm not going to touch it. So you can do unit balls or Banach spaces, Banach spaces with various kinds of additional structures coming from probabilities, so the algebras, variables, dynamic groups acting on probability state or probability algebra theory. There is an entire program of people studying regular algebras of various kinds. And then there's also the abstract tools, generalized part. There are a few things that don't and can actually annoyingly tricky, but most of the general toolbox actually generalized. Okay, so this works. Okay, fine, happy. What? Okay, so next, why am I interested in non-community? Let me give you 3 possible motivations. Okay, so the first one is these quantum questions I referred to earlier. So I use the term question today just basically it's something I can measure about. I ask something about an object, I measure property of an object. Okay, so for us, this would be a logical formula in variable that represent that object. Only, as I said, in quantum mechanics, the question I'm going to ask, the things I'm going to measure is what they call observables. And in this Draco-Neumann formalism, they are represented by operators on a bigger space of states. And these operators need no proofs. So if we even want to get close to that, we need to consider logic in which formulas. So that's one. Actually, I mean, obviously I'm not the first person to have thought about this. For Neumann himself, So there's a very old paper, highly cited, because it says, okay, something a bit different. So if you do propositional logic, classical propositional logic in a Boolean algebra, okay, Boolean algebra is essentially a lattice result. Okay, so now if you look at the set of projectors on the Hilbert space, these are family of operators, but they actually form lattice. So if we just the lattice of closed subspaces of the Hilbert space. So you can do propositional logic in that. Okay, so for me, there are two problems with this that things that bother me with this. First, that this lattice is not distributive, so that means that all the usual identities you would expect to hold don't hold, and that means that there are many more connected that you can construct than in usual Boolean logic. So it's interesting. And the reason it's not in between is also because this lattice is actually not continuous. The operation, lattice operations that meet and destroy are not continuous. Just think about projection on two lines. If the lines don't coincide, the projection is just on single, the intersection is just a single point, but then as the line maybe get closer and closer to be the same, but still a single point, but at the limit when they coincide, it's a line. So the point of this continuity there. So okay, this is not going to be continuous. Okay, so okay, I guess in some sense for me, I would just something. Okay, and I guess in some sense, in some ways they will do something different. And there's something you're just curious about. So let me explain why there's just healthy curiosity reason to look at this. So let's start by looking at continuous first order logic. So the second formula says fixes it fixed variable. So the second formula has input variables, okay, completed for obvious subnorm, and that's going to be something like the continuous functions on some aspects. Actually, on space. Okay, so if you complexify this is the set of complex functions on that compact set, and that's a commutative system. So in some sense, that actually would make it a little bit more precise soon enough. Continuous logic corresponds to commutative unital system algebras, and really in the same sense that classical logic corresponds to Boolean algebras, and okay, reduced logic corresponds to matrix algebras. You can formalize this correspondence, and then you can ask, okay, so that logic will correspond to unital system algebras. Curious. Maybe there is no answer. I don't know. That would be. Okay, so let's go to something. Let's say it's going to be valuable. The first step is easy. So the first step is syntax. What is syntax? What's going to be the syntax of non-commutative first order logic? Okay, I'm going to start with atomic formula. That's going to be predicates variable. If there's no other formula to be. And then I'm going to close out like this. So addition. Non-commutative non-implementation, okay, sorry about that. I'm going to, so again, in C-star algebra, so I'm using the star operation, the adjoint. And, okay, and real complex. And then I want modifiers, sup, and inf as. Okay, great. I define syntax, can I go home now? Of course not. This makes sense. I mean, this is meaningless unless I give some meaning. Okay, so let's forget the question of semantics. And how do I give meaning to this syntax, to this form? So first of all, okay, I'm going to give two interpretations of what I mean by semantics. First of all, semantics definitely should tell us which formulas, for example, coincide. Tell me, who does the formula? two syntactic ways of saying things actually say the same thing. And actually, I want to do that. I want to order on formulas. I want to know when one formula implies another semicolon. So, okay, so how can I do that? So I see roughly two main paradigms for doing that. So one way is kind of the easy way. Define structures. Okay, so in continuous logic we define structures. In classical logic we define structures. Then we just on the structures observe which two formulas just always give the same interpretation, so they are equivalent, or which two formulas, one always has a lesser interpretation than the other, or in Boolean logic, falser interpretation than the other, then there is dissatisfying relation, and that's it. It's easy. But sometimes you just have no clue what structures to be. And actually, I'm in that situation. Or at least I was in that situation. So I want some things like, so another way of specifying semantics. So let's call this algebraic or reduction semantics. So let me explain. I want to specify, so in order to do that, I need to specify the category to which the algebras or formulas belong. It should be a category of all the structures. So for example, if I say I want them to be Boolean algebra, then I'm going to, I expect to get classical. Every algebra with Swiss logic, if I say community between transistor algebras, okay, that will actually order the if I look. Okay, if I look at the self-atomic members of those algebras, this is the code space, and it gives me continuous form. Okay, and the point is that I call this deduction semantic because we can really do it by a form of deduction system that tells you, okay, we're going to end up with something that's a Boolean algebra or a Heisenberg algebra. And since I don't know how to do the first, at least not yet, let's do this. Okay, so I want to specify the category of algebra or formulas, and that's why do I do it? Maybe it's more explicitly why I do that. Okay, so this is going to tell me how to interpret the connect. This is going to just need to be operations in those algebras. If I say I want community, I want non-community. See, star algebra that means I can interpret multiplication by multiplication, adjoint by adjoint, addition by addition. It tells me how to interpret the connect. Next thing about it is that it also allows me to, it also tells me how to interpret the quantifiers. So, I mean, I guess that if you ever thought about it, it becomes obvious. But let's see. So let's say that's in classical logic. I have a formula in two variables, x and y, two tuples of variables, and I have a formula in just the first variable, psi. So I know that psi is lesser than for all y phi. Psi implies for all y phi. Because y is not free in psi, this is exactly the same that just psi implies phi. And actually, if I know that, that tells me exactly where I put for all y phi in the order on Lx. So actually, this defines to me the quantifier for all y phi. So this is the way we define quantifiers as what's called an order action. And you can do this also in, you don't really do this in statistic logic. You can do the same thing for the derivatives, just do the same for there is, order, and the same thing in logic.
I think there are some problems. We cannot hear you, unfortunately. Like for like 10 seconds, we can't hear you. I don't know if you can hear us. I wonder if. Yeah, maybe I will.
We can't hear you. Działa? Dobra. Jarku, napisz maila też.
Okay.
I'm sorry, something happened.
Yes, we couldn't hear for like a few seconds, and then you just disappeared.
Yeah, okay. There is a problem. Okay, maybe let me turn off. It actually occupied too much memory on my computer, and I'm afraid it might happen again. Something about, okay, let me turn off the camera and hope it's better. I'm not sure.
Okay.
Okay, let's see. Do you see? Oh, no, I can share it. Share it.
Okay. I also turned off our camera so that maybe there won't be any problems furthermore.
No idea. Let's hope so. Okay. I'm sorry. I'm not using it's to navigate the crash. Okay. I'm sorry. I'll try to. I'll try to go on. So you can use this order. So the order tells you how you can modify. So basically, once you know this category of order structures, you know it. Okay, so let's do it with non-commutative logic. So I already have syntax. So now I'm just going to say, take all the syntactic formulas in some variable, and I want to generate as quickly as possible a C-star algebra under certain constraints. So first of all, there is the constraint. I have any of those bounds, I think it's generating elements. So I know what bounds I want to impose. The norm is less than bound. Connectives are interpreted as the C-star algebra operations, as I said. And I want the modifiers apply to self-adjoints to satisfy, to be these order items I described. And I only really can interested in modifiers apply to self-adjoint formulas. So if formula is not self-adjoint, it's just applied to applying self-adjoint. You just have to have it. And do the same thing with integral and maybe possibly add addition. So this is as the total now you can add additional constraints and size. And you get what you would expect to be the algebras or formulas modulo that. And the point is that if you take this formula just to replace C-star algebras with any of the other algebraic structures I mentioned, you get the corresponding. So this is really a completely general scheme, a very easy scheme to just define it. Okay, so fine. Now I didn't find the semantics, so can I go home? Well, okay. Well, no, because I mean, I don't know what the structure is in this logic, and it doesn't do that purpose. For many years, and I tried various things, tensor product of the and the idea of how to get around that problem came from some recent work with Tomas Valencia, for example, based on earlier work by Senator Badiri about that. So let me tell you a little bit about that. Not just the very. Okay, that continues on. So we said it's generated by quantifiers to the nth and continuous connectives. Okay, restrict the set of connectives to just a fine operation. So add, multiply by a scalar, okay, in added constant. Okay, you get a fragment of continuous logic, and you can define models, so you define structure interpretations exactly as it would be tested, and this structure for the use. And we wrote a very long, so really by doing all this linear logic, we proposed for various reasons, we wrote a fine logic, we wrote a very long paper, which mostly concentrates on a special kind of model of affine theory, the extremal models. I'm not going to define immediately what an extremal model is. I'm going to define indirectly soon enough. And okay, we did that work. We had lots of okay, so let me put now this logic in line with all the other things that I mentioned earlier. So we know the structure of semantics, the easy kind of semantics. So what kind of algebraic semantic does it give? What are the algebras of formulas? Well, they're exactly complete order unit space. What's the complete order? Right? So you take the real ordered bar space, and assume that it has an ordered bit. So an ordered unit is something that defines, okay, so that okay, this is the group. Okay, so the norm is basically what multiple of the order you need in order to catch the element. And if this is the norm, it's a complete norm, then you get classical definition. Okay, and that is exactly so. This is the category corresponding to affine logic. So if I look at the set of formulas in this fixed variable, this is a complete order in space. And if I do this reasoning I described earlier, if I do the reasoning that I described earlier about basically constructing somehow the freest project in that category, you get exactly that. So this is it. Okay, how does this help us? So here we get to the simple. I get to the database in a sense. The point is that from a categorical point of view, C-star algebra sits neatly between community C-star algebra. The reason for getting factor from community C-star algebra to C-star algebra, so there. And I guess it's almost a forgetful factor from C-star algebra's unity. C-star algebra of the spaces basically restrict to the self-algebra. And actually, you can recover the entire C-star algebra from that and various extra information, but don't forget also that extra information. So what's left is a real Banach space with a big limit of the C-star algebra, and it is a complete order space. Okay, it will be the order on the self-algebra, of course. This is the complete order. Okay, so it really sits between two forgetful factors, using forgetful factors between these two categories. So in particular, if you take a non-commutative logic, so if you just set this various algebras and formulas, and you apply this forgetful factor, you get an affine. So maybe that means it. Okay, so I'm looking for structures. I want to know what's the model. So let's see what's the model in affine logic in this formalism. So as I said, okay, if there is this formalism, then you just kind of crunch things around and realize that it's consists of a set A. So from this you construct L of A, the algebra of formulas with parameters in the model, a non-free variables. So this is going to be a order unit space in this case. And then you want a state on that. So that's going to interpret addition and content, as I'm functioning did that correctly, but I also want to interpret the quantifiers. And so I just going to add this requirement. I want the interpretation of a quantified formula to be the supremum of the interpretation of possible interpretations of that formula as y values of this function. That would be obviously. And now I can tell you what an extremal model is. Setting in this way, an extremal model is still very important for Tudor and master is just an extreme state of this. This set of states is a compact convex set. It has its 3 points. Extreme states are exactly the extremal. Okay, so can we use this to define non-commutative models in define non-commutative model? Just say, okay, I have a non-commutative object, so it's in particular a defined logic, so just say a model that's fine. But if it were just this, it would be kind of disappointing, I guess. But still, the answer is almost, he definitely gave me the right hint as to how to, say how. But so let me give you the definition and then explain why it has from time. So I'm going to take a little bit first of all. Okay, so the model of L, so again, it's going to be a set of points. Okay, and now there is new kind of information that I didn't have before. I don't have empty space, H, and the representation of, so L of A is the unital C-star algebra of all formulas with parameters in A and no variable, and I want to interpret them in BOH. So I'm going to have a representation of C-star algebras from L of A to the C-star algebra of BOH. And now I also want this thing about quantifiers. Only here I have not one state, I have lots of states. For any unit vector, I can define a state on the algebra, on my algebra using the vector and the representation, and I want all these states to interpret the quantifier. Again, this is a definition. If the state of a quantified formula, the suit has to be the suit of all possible states of instances of that formula as given. Okay, again, it's kind of natural. Okay, easy to do for anything. Oh, and by the way, let's add the definition. Say it's a pure model if pi is usable, which corresponds to pure states. Okay, not that important. Okay, so first of all, let me state that this definition is useful in the sense that it corresponds exactly. So I already had algebraic semantics, and now I'm defining structural semantics, and I'm claiming that they coincide. So that means that if I have a non-zero sentence, so there is no algebraic reason that it should be zero, there is no deduction that it's zero, well, then there is actually exists a model, even a pure model, in which it's not. This is the complete theorem for this algebraic reduction. And just a small remark, if L happens to be commutative, so should be continuous logic basically, well then a pure model in the sense that it doesn't define is just the same thing as the model in the sense of continuous logic. Basically because it's commutative, so representation has to be one-dimensional and okay. So I guess I want to say what way maybe to justify why this theory is true, why this definition looks reasonable. So, as I said, the hint in some sense comes from this time logic. So let's start, as I said, let's start with non-commutative logic. Forget that it's non-commutative logic, so all that's left is an affine logic, and take a look. Okay? So that's just the state. Okay, so I have a state on, okay, now let's remember again that it was actually to begin with a non-commutative logic. So I have a non-commutative algebra formulas, and I have a genus. So just note that if I have a state on something, usually in unique fashion by representation in some Hilbert space and a vector in the space, a unit vector in the space. It's unique, if the vector is generating, then it's unique up to unique. It's really unique. So, and moreover, the state is pure if and only if it is a representation. Okay? So if I start with a state on L of H, that have an affine model, so that's a state on L on formulas with parameters. So that gives me a representation. Okay, but there is a problem because this representation gives me, okay, there is this one vector in H that corresponds to the state that's a certain good state, but there are lots of other states. And why should they be good? And if they're not, it's kind of, it's not very. And I guess the one thing that convinced me that there is some hope for this direction is the fact that actually we show that all the other states are automatically positive. So let me explain roughly why that's true. So basically what you need to show in the following proposition, it's not completely obvious, but it requires some. So basically you want to show that if you want to conjugate the formula by some other formula, and that other formula does not depend on the variable by which you quantify, then you can push the computation inside the formula. That's like outside, inside, it gives you the same result. Okay, so this is what I call invariance under conjugation of the formula. Of course, y cannot be free in this formula. That's the only one. So there is one inequality that's completely immediate, and therefore if I is invertible, then actually equality is immediate, but if I is not invertible, the general case applies. Now, why does this help us? Because, well, you see, I start from a state that corresponds to 1. Now, if I have another, this vector is general. So, okay, if I have another vector, then I can approximate it by something that I can reach using the action of my C star. So what does it tell me about the states? It tells me that the corresponding state is obtained by composing this conjugation, putting the original state with conjugation by that formula. And basically now, because this conjugation kind is just a formula with parameters, with no free variables, so I can put it inside the quantifier, outside the quantifier, it doesn't matter. So any property by the quantifier that psi has, the zeta is going to inherit. So I guess the next slide is a very detailed proof of that. I'm not quite sure I want to do this, but basically, just look, I mean, okay, the zeta state of the quantified formula is obtained by conjugation on the psi state of the formula, and that conjugation can go inside the quantifier. You know that psi states respect quantifiers, and blah, 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 blah. You deduce that the data state also respects. don't want to go into more than that, just longitude is what it's, but that doesn't work. Okay, so that means that if I start with a model of a fine logic, I actually do get a model in this more in the non-commuting sense. In particular, if I know a completeness theorem for a fine logic, and I can use a completeness theorem for non-commutative logic, and well, I do know a completeness theorem for fine logic. So I use this completeness theorem for so that might explain why I want such structures. Let me say just one last technical thing. I was actually quite surprised, but you can get Kleenex forms quite easily in non-commuting logic. So what is the statement? So quantified formulas are always going to be self-adjoint, basically by definition. You find them in the order. The order is self-adjoint, so you don't take every formula to be a Kleenex form, but okay, so self-adjoint formulas or the self-adjoint part of any formula is going to, you're going to be able to write it in terms. So how do you do it? Basically, it's the main structure of the argument is essentially the same as in classical logic or in continuous logic. You want to push connected inside. And addition, you can do that, it's easy, it's monotone, so that's not the problem. So really the one and if you want, as I said, quantified formulas are self-adjoint, so adjoints doesn't play any role. Okay, so what's that? Multiplication. So I take a formula, do a quantifier, I multiply by another formula, and I want to push that formula inside. Now, already in continuous logic is not entirely immediate because multiplication is not monotone. So, according to the sign of psi, you might need to change the quantifier from sub to if. So, you can just do this as you can for addition. But okay, that's already continuous logic, so now in non-commutative logic, wow, okay, but actually it's much easier to make progress first. Okay, so first of all, I said I want the self-adjoint part, so let's take this formula and we calculate the self-adjoint part, so it's the average of the formula in its adjoint. The supremum itself is self-adjoint, so there is no start there. And you can express that actually as a difference of three conjugated formulas. Okay, now conjugation, you can push inside the quantifier. That's exactly the direct side of conjugation. You can put that inside the quantifier. Okay, and now all that's left is to deal with addition or subtraction, so we can addition, and I know how to do that. So I can do this. And you might get an extra quantifier alteration because of the fact that you have subtraction here, but okay, you expect to get an extra quantifier alteration because that you already have that in ordinary continuous. So this is one of the most interesting things I realized. So things start falling in place. This is all extremely recent, and I guess the thing that I still haven't gone through definitely as much as I would have wanted to is examples. I think the one example that definitely has to be looked at is to understand what kind of non-commutative logic is generated by the different symmetric groups. So you want basically permutation of n elements to be an atomic formula and see what kind of logic is generated. I spoke with Isaac Goldbrain. He's more interested in various quantum X, quantum this, quantum that. Maybe this is also going to be an example of that one. Okay, this is question of metric. I completely intentionally omitted it. It's a bit more complicated. Things can be done about this, but okay, that's still, it's less obvious that you continues or finally. Okay, what about knives? I mean, you do not have a duality, not really sister algebra is not the dual of the topological. So there is no types, then that's another apart from that. Okay, if you want types, maybe pure states, but then these also not only depend on your element state, it also it also does depend on the state in this institution. So it's a bit more, it's going to be more complicated. Everything is going to be more simply. And of course, you cannot speak about meeting type before you speak about nodes. And I think a very interesting thing, as I said, I don't know quantum mechanics, but I'm kind of from the very little you know, it looks like H, this symmetry should correspond to a space of quantum states of something. Okay, what should this set of elements be? Particles, and then measure properties of particles. Okay, this definitely merits some thought. But I mean, for me, the original motivation was just pure curiosity, and it's just starting to get satisfied, and this is the good one. So, thank you. Thank you.
All right, so thank you very much for your talk. And now there is an issue with the microphone. So the microphone, there is only one microphone that you can that can be used so that you can hear the questions. So I'll try to do my best to repeat questions from the audience. Okay, so are there any questions? All right, so then let's thank the speaker again, and thank you very much.
All right. Okay. Dobra, to teraz tak. Teraz przechodzimy do tego. Dobra. No, pokażmy to jeszcze na sekundkę. Dobra, to transmisję kończymy. Przejdźmy do kamery. Ja teraz zainstalować studio, żeby się bo się zainstaluje to, to nigdy nie może być kamerą. To jest cała tak jest